Hi everyone, seems like it's time to start. My name is Oleksiy Ruch, and I am the head of SpaceTech Analytics. First of all, I want to thank all the experts who are joining us today. It is a great honor to host you and your fascinating presentation at our event. I'm also grateful that we have hundreds of listeners who understand the huge potential of the new space era and are eager to learn about most cutting-edge technologies in space mining. A few brief words about Space Tech Analytics. We are a strategic analytics agency focused on markets in the space exploration, space flight, space medicine, and the satellite tech industries. Our services are designed to provide key strategic recommendations and guidance regarding space-related technologies and techniques within the reach of companies, other entities, and nations. What helps optimizing their own action plans and strategic for opening the new frontier, providing specialized guidance for business and investment core decisions. Space-related technologies are being developed at a rapid pace today. New launch systems, satellites, propulsion, manufacturing, and other companies seem to emerge every quarter. We have explored every planet in the solar system, including Pluto, despite the fact that Mike Brown tried to kill it. We are standing now on the brink of the next chapter, space development and ultimately settlement. We are approaching a time in which we won't have to exploit the planet anymore. Earth may become once again a garden. There are millions of opportunities in space in terms of mining, material resources, and energy. So we are pleased that today 10 people will share their visions with us and how we are going to make it happen, we as humanity. And Rand Simberg will moderate the conference. He is a recovering aerospace engineer with over a third of a century of experience in the space industry. Rand has written about space policy and technology for many publications. He also advises on regulatory and market issues pertaining the commercial and personal space flights. Rand, please, it's your word.
Thank you, Alexei. Good morning or afternoon or evening, depending on your time zone. I'm very pleased and excited to moderate this event to see so much interest in it. For over 6 decades up to the present, everything that we've used in space, hardware, water and air, propellant, had to be launched there from the home planet at very high cost. We're on the verge of vastly increasing our activity levels. And despite the fact that launch prices are coming down, thanks to disruptive launch technologies and competition, ultimately we're going to have to learn to live off the land if we're going to develop and settle the solar system. It will simply be economically untenable to have to rely on imports from Earth for bulk material to supply facilities and settlements on the moon, Mars, other celestial bodies, or in free space. Fortunately, the solar system is rich in the resources we will need to not just survive, but thrive off planet. The next challenge is how to utilize them, both to create an in-space economy and to expand the economic sphere of Earth and life itself out into the solar system, to echo the late John Marburger's words in 2006 when he was George W. Bush's science advisor. Accordingly, SpaceTech Analytics has assembled a group of some of the top experts on the planet in space mining to provide us with some insight into some of the ways in which we're going to do that. Because we have several speakers today and finite time, there will be no questions until after all of the presentations during the panel discussion. But feel free to post questions in chat. We'll try to get to them afterwards. And the questions, please address them to the specific speaker unless it's a general one for all panelists. For the same reason, I'll be very strict with the timing of the presentations. I've discovered a new feature in Zoom that allows you to melt down the camera and mic if somebody doesn't get off the stage on time. So with that, I want to introduce our first speaker, John Mankins. I've known John for I don't know how many years, decades. But John is president of Artemis Innovation Management Solutions, LLC, and of Mankins Space Technology, Inc. He's also vice president of the Moon Village Association and serves on the boards of both the National Space Society and of Space Canada. And most recently, he's joined the faculty of the online Kepler Space Institute. During his 25-year career at NASA and JPL, he held numerous positions, including serving as chief technologist for human exploration and development of space at NASA headquarters, where he received the National Exceptional Technology Achievement Medal and managed the $1 billion per year Exploration Systems Research and Technology Program. John's best known for writing in the early 1990s first detailed definitions of TRLs, technology readiness levels, and as the world's leading expert in the field of space solar power. He lives with his family on a ranch on the California Central Coast. John.
Thank you, Rand, for that kind introduction. It's a real pleasure to be with such a distinguished group of thinkers and visionaries on in a discussion of what I think is going to be a very important topic. This morning, my topic is going to focus on lunar south polar mining as a subset of the larger topic of space mining and space resources. And I thought I would begin with past visions, going back to Jules Verne in 1865 and the From Earth to Moon, which was extraordinarily prescient, sending the first human mission from Earth to Moon with a launch from Florida. And then after some lunar adventures, a return to Earth to splash down in the ocean and be picked up by a US warship. Almost exactly the same end-to-end mission concept as was actually implemented 104 years later. A key factor in the Jules Verne vision was that it was a private venture. Later thoughts about the moon included the idea in the 1895 of lunar gold mining, and in the extremely beautiful and visionary German silent film Frau und Mond in 1929. Once again, the motivation for a private venture going to the moon was space resources, the idea that there might be gold on the moon. And so from the earliest days of at least fiction, there has been considerable interest in the moon and its resources. In 1963, in explaining the venture to go to the moon within this decade by the United States government to the US Congress and the American people, a beautiful small booklet was put together. If you have not seen it, I highly recommend it to you, called Why Land on the Moon. This was in 1963 by Dr. Robert Jastrow and Dr. Homer Newell. And it has these beautiful etchings of what the lunar mission might look like, and explained the purposes of going to the moon as relating to understanding the origins of the Earth-Moon system, understanding the origins of our solar system, and to essentially develop new technologies and capabilities, and to establish on the geopolitical stage that the US was in fact a country with whom to partner and whose system of government and economics should be followed. This was, of course, in the midst of the Cold War. Today, some 50 years later, there are dramatically different motivations for the moon. And in large measure, these are driven by the resources that have been discovered over the past couple of decades at the lunar south polar regions and the lunar north polar region, having to do with lunar ices. Just as an indication of the reflection of this global interest and consensus, this is the current membership of the International Space Exploration Coordination Group, which is responsible for coordinating between activities, putting together an overall roadmap for space exploration in general and the lunar exploration in particular. And you can see, and I should mention that in the last year, the number of countries participating in this coordination group has doubled. That's currently chaired by someone at the Canadian Space Agency. And in the global exploration roadmap that this international group has framed, the idea of space resources, lunar resources, lunar ices loom large. In particular, in their global exploration roadmap, published a year ago next month, there are two key requirements, two key goals that are identified. One is a target to produce 50 tons of propellant per year from the lunar materials. This is an ambitious goal. And the other is to generate some 300 kilowatts of power on the lunar surface for a variety of lunar activities, including resources processing. And I wanted to probe today in my remarks these two numbers: how much propellant and how much power. And so I'm going to come at this from the standpoint of a design trade space and some activities that are currently being conducted by the Moon Village Association. So from the standpoint of the trade space, there are a set of requirements and constraints. For example, recent discussions having to do with the science of the permanently shadowed regions, which is where the lunar ices are, the question of whether or not and how much environmental contamination might be acceptable, and of course, for any kind of private venture, the ever-present minimization of cost. Of course, what's the principal driver here is the production of H2O from lunar PSR regolith. One key trade space question is, where do you do it? And there are a number of recent developments. I think perhaps George Sauer in a few moments will talk to one of these that have to do with processing from the regolith in the PSR. The case that I'm going to look at today in just a little detail, but from the standpoint of the requirements, is really the idea of having a remote facility, a refinery, where the processing takes place rather than in situ in the PSR. And of course, there are several different means that have been looked at, including a couple of different types of thermal extraction, either using reflected sunlight or using powered heating. And then, of course, there's the idea of doing it at a remote location. In the past, a number of different fun concepts. The idea of the 1980s of a big open pit mine on the moon, as executed by Pat Rawlings. Another Pat Rawlings image, which is the idea of building power stations around the rim of a permanently shadowed crater and transmitting power down into the darkness. And also the idea articulated in this image in the lower right by Bob McCall of a roving lunar concentrator. Of these images, of these concepts, I think only the idea of transmitting power down into a PSR from power stations around the sunlit rim is still very much in discussion. This is a concept from a recent NIAC study, and it's one that I won't second guess, but I'll speculate that George Sauer might speak to this. It's the idea of in situ processing of the lunar regolith using reflected sunlight and a dome to encapsulate the regolith. And then, of course, there are a variety of concepts having to do with centralized mining equipment and mining machinery. You can see in the cartoon in the upper left two radically different kinds of mobility system. One, a more or less conventional track layer tractor. I think that's impossible, but nevertheless, it's a nice picture. And the idea of a multi-legged athlete, the JPL athlete type roving vehicle doing in situ fabrication using regolith. So with regard to terrestrial mining, this is the direction that terrestrial mining is going. It's going all electric. And these are some images that I grabbed from online sites in the last couple of days, which reflect this new direction for mining. As the world drives towards carbon zero systems, mining is one of the areas where enormous amounts of diesel fuel, a lot of CO2 and methane are released. And so the mining industry is trying to go all electric. And that includes electric machinery, such as in the lower left, It also includes electrical transportation, such as trolley lines, but also electrical equipment down underneath the earth. And one of the forerunners in this, who you'll also be hearing from later this morning, Jim Caravella, is Off-World. And in this case, an all electrical fleet of modular, smaller robotic systems is being developed to do terrestrial mining, and also in the longer term to do mining on the moon. And I think as a vision, this is a real leading concept to transition from the all electrical terrestrial mining to all electrical off-world mining, pun intended. So now to the question of the study that we're doing within the Moon Village Association and these two key numbers: how much propellant and how much power. So this is a high-level context for the lunar village of the Oasis 2045 case study that the Moon Village Association is doing. It shows the region to the between Shackleton, the Gerlach, and Sverdrup, the lunar South Polar Ridge, which is one of the relatively sunlit locations at the South Pole. This is a location that NASA's looking at as one of the places where the first or the next human landing might occur. And the concept is to place a settlement at sort of in between three of the four major ice-bearing locations. One, this diamond-shaped area above, two, de Gerlach, and three, Sverdrup. These are just some terrain maps of the locations in question. And in looking at these, it appears that there are pathways such that surface mobility, surface access to each of these three sites is achievable. I don't include Shackleton because the Shackleton crater is extremely steep. The difference in elevation from the rim of the crater to the floor of the Shackleton crater is on the order of 5 kilometers over a distance of about 6 kilometers. I don't think there's any reasonable expectation that in the near future that surface access to the floor of the crater is going to be tractable. But from these other locations, for example, I show here a notional route. It should be possible to go from the central processing refinery envisioned at Oasis to the three ice mining locations that are indicated. This is just a zoom in on the habitation site and this end of the lunar South Polar Ridge. In particular, this crater is the location for the Oasis 2045 habitation that we're looking at. Across the ridge and safely about 4 kilometers away is a location that we're looking at for a spaceport. And in between these two, there is an impact feature, which is very interesting, which is essentially never gets above about 100 degrees Kelvin. It's not a site for ice because it does get a little bit of sun, but I think with just a little bit of engineering, that this hole could be turned into a cryogenic pit. And the idea is to offset the requirement for energy to liquefy LOX and hydrogen by making and storing cryogenic propellants in a pit. And therefore, you don't have to provide the energy otherwise. You just need to provide the radiative cooling. This is a same locations, but showing a beautiful false image made from the Lunar Orbiter Laser Altimeter data of the Lunar Reconnaissance Orbiter. And this is available at JPL if you want to go and look at it. You basically see the whole moon with LOLA data. And and this is just a zoom in of this particular location. You can see the pit here that we're considering for a cryogenic propellant depot. And the beauty of this is, of course, it's at the far end of the lunar South Polar Ridge, is that there is a trail all at about 1,575 meters elevation from the settlement to the pit, to the propellant depot, to the spaceport. And so you can envision cutting a road along the ridge line and have a flat road with no bumps or rises or falls from A to B to C.
How many more, John?
Oh, I'm coming right up on it.
Okay.
So here's the concept of operations as I described: a central facility for the spaceport. This is a model that's been developed for putting together an integrated analysis of these various elements. The two case studies that I mentioned, a lunar travel and tourism propellant use case model and lunar agriculture use case model, basically walking through what are the various stages of going from regolith to refueling a vehicle and regolith to having water for agriculture. This is the reusable lunar lander case, and I just wanted to highlight that that it works out to be approximately 180 metric tons of regolith per reusable lander launch, with a presumption of about 9 metric tons of LOX hydrogen to carry a payload of about 8 metric tons. And that works out to about 450,000 kilowatt hours for each launch. And if there were 2 launches per month, that's a requirement for about 1.5 megawatts. So the 50 metric tons that was identified is a good number. The 300 kilowatts is probably on the low side. However, for the lunar agriculture case study, I won't go through all the details of how many square meters per person, but just suffice to say that for a modest-sized lunar settlement, for each person, you need about 1,250 square meters of agricultural land, and that requires approximately, assuming that the regolith is 5% by mass, water ice requires about 10,000 metric tons total for the agriculture. For 40 settlers, works out to be about 25 million kilowatt hours. But if you do it over 10 years, only works out to be a power of about 300 kilowatts. And so the power needed for the agriculture is much more significant. Closing, for an integrated lunar spaceport and settlement, the architecture suggests that a common family of rechargeable electric vehicles can do the mining, the regolith hauling, and so on. The transportation, i.e. taking the ice-bearing regolith from the ice mine to a central refinery rather than processing it in situ, only represents a tiny fraction of the total energy required for either of these use case models, on the order of 14%. And so given the other elements and convenience and so on, it seems like a worthwhile option. And it would facilitate a set of strict protocols to capture science data while you're doing the mining and to minimize any release of volatiles, because the actual processing at the refinery would be done within a closed environment. Additional studies are underway and will be presented at the upcoming IAC 2021 in Dubai.
Thank you, John. That's great. Good introduction, good history for a lot of people unaware of it, unfamiliar with it. Our next speaker is Dan Sachs. He's from the Great White North, co-founder and CEO of the Canadian Space Mining Corporation. He's an entrepreneur and angel investor with a deep background in real estate investment, finance, and development, and a strong acumen in both private and public capital markets. He's actively participated in over $4 billion of real estate deals across Canada, the USA, and Germany. Prior to CSMC, Daniel founded Sensi Properties, the first cannabis real estate investment company in Canada. Daniel has a passion for bleeding edge industries, obviously with high degrees of uncertainty. He's a director of Bordeaux Properties and advisor to BIGG Digital Assets, Hive, and Fieldhouse. He has a master's degree in real estate from Cornell and a BA in economics from Dalhousie.
Thank you very much for the introduction. I'm very honored to be here. I'm going to attempt to share my screen at this point. So I'll try and keep this relatively quick and timely. I'm certainly not one to be giving with any qualifications to be giving a technical presentation. So I've really focused around kind of the economic development story, both from a Canadian perspective as well, from a global perspective here. So the Canadian Space Mining Corp is a lunar regolith mining corp. We were founded to process water and for fuel in situ, as well as oxygen and kind of other things. We think in getting there to building a mine on the moon, along the way, we have to build a lot of the infrastructure in the gaps that we see in the market. And in doing so, we think we can accelerate the entire kind of ex-Terran and lunar economy, benefiting humanity for generations to come. So, you gave it a great introduction to me. My partner is Dieter McPherson. He was most recently with Aurora Cannabis. He came in when it was about kind of 60 people and about to go bankrupt as a public company, took it and scaled it to 3,000 people, building the largest, most sophisticated agriculture facilities on the planet, teaching himself, a mix of kind of automation, robotics, project management, which fundamentally we believe that a lot of this is about project management and systems engineering, not about kind of new technology. We think a lot of that already exists. Our experience within the cannabis industry may be, a bit of an odd duckling, but quite frankly, we think there was a lot of regulatory uncertainty within that industry, and that skill is quite applicable. Team-wise, we brought in Mark Donato, who's the former COO of MDA, was known as a turnaround guy within MDA, turning around their Montreal and their Brampton facilities when they were about to go bust. He's done and led kind of some of the largest, most famous space projects in Canadian history, including, Canadarm2, Canadarm3 bid, the Mars rover that was built for the CSA, among others. So we think there's a lot of kind of depth there and certainly engineering talent to build around. Our advisors include the former head of autonomous mining or emerging technologies for Volvo Construction Equipment, one of the co-founders of the X Prize, former chief technologist at NASA, and the former CFO and director of MDA, among others. So we think that, we've got a great orbit around us of people. We are a young startup, so we've been around for about a year and are just in the process of kind of scaling. Values wise, that's an important thing for us, certainly first and kind of foremost. So we value being pragmatic, first of all. This is not about running kind of science experiments, and this is not about, trying to find the best way of doing things. It's actually just about getting stuff done. We think really this is an implementation problem kind of more than anything. Trust and transparency is key. It's key for us to be working with partners. This is not something we're going to do alone, so it takes a village. This is about us working with others, both domestically, internationally, at multiple levels, and all are welcome. We think that one of the key strengths of Canada is its ability to work with other countries, and we think that is a strength here. And then treading lightly, we think it's important that mining, resource extraction space be done in the most responsible way, most sustainable way possible. And we really think that's an area Canada can lead in, an area that, it has led in within the mining industry. So as you all know, we're returning, to the moon to stay in 2024. And we think that Canada can play a key role there within resources and infrastructure. We're really focused on the moon because, quite frankly, we think that the gravity facet, of microgravity, of 1/6 gravity, allows it to be scalable in the way that asteroid mining is not scalable kind of at this time. It allows us to adapt Earth mining technologies and also to build and develop infrastructure that remains there in a way. It's a known body, and there's a lot that we know about it. There's obviously a lot that we don't know. That's what we think is kind of one of the biggest areas of opportunity, and then there's new rules, with Artemis, countries legalizing, and there's really kind of a snowball effect happening that we can see that the, inertia is kind of moving in the right direction. There is not the regulatory clarity that is needed now, but it's clear that that's happening. And certainly with what's happening with, the US, China, and everything like that, it's going to happen in the next couple of years. I don't know how that works, but we're going to have to kind of navigate that. So timelines, previous kind of space mining startups, the last generation, a lot of the reason that they went bust and was quite frankly because the timing just didn't make sense from an investment capital perspective. And now within this window where NASA wants to start mining in 2025, the Chinese are establishing a moon base in 2025. And we're looking at, building a moon mine in kind of 2030 and working back from that date. We think this is actually a reasonable investment horizon in a way that it wasn't previously. If, it was 5 years ago, the investment horizon was a little long, and now it starts to make sense. Quite frankly, these are aggressive timelines, even for mining on Earth. So, there's a lot of pressure there, and certainly it's a big challenge, which is what we like. So our approach is really, almost like a private space agency to work with academic institutions for tech transfer, R&D, prototyping, utilizing infrastructure that already exists in laboratories, et cetera, and technology solutions that have been, problem solved, but need to be scaled, working with industry and strategic partners. So we're out there looking for and talking to strategic partners. And then, of course, working with governments and various space agencies in order to go after this. This is something that is larger than any one group. And so this is really about cooperation. And that's really kind of our business model. So, from a phase mission timeline, what we're looking at is, we were in kind of startup phase over the past year, forming, advisory team partnerships. We keep, bringing on people because fundamentally this is, a capital and a human capital problem. We need to throw the right brains at it and have the money to fund that. And then 2023, we're working on towards our first mission, which is a survey mission, identifying key points of interest. And then phase 2 was really kind of a rover mission, if you want to call it. I would call it a mining equipment mission, to kind of beta test that technology. Ideally, we want to kind of, perfect some sort of extraction there at some level, some micro level. So, it could be a gram of water. It doesn't need to be, 500 liters of water to prove out those technologies within that value chain, and then working back again from that 2030 operating date. So Canada's leading position, really Canada is kind of the leader globally within the mining industry now. So there's a ton of depth of human capital and expertise, probably more so than anywhere else on the planet. We think long-term that positions Canada to succeed here. We are obviously late to the game as a country within space mining, but from a long-term view, we're okay with that. We have tons of aerospace expertise, and particularly in space robotics, which we think plays quite well to what needs to get done here. And then, it needs to be said that Canada's oil and gas industry has gone completely sideways, as I'm sure, many of you know. So we see a lot of stranded human capital as well as capital equipment that can be really redeployed and retooled. That's part of that story here. And a lot of those people have worked on building some of the largest and most complex infrastructure projects on the planet. And so we do think there's the right elements there. And then, Canada is home to the largest capital markets for mining in the world. This is where you get mining financed right now. There are other places as well, but it is really the dominant place. And there are structures, legal structures within that, like flow-through shares, that are quite beneficial to financing that industry and provide a strategic advantage. We think that those can be kind of updated, and us and others within the country are working on adapting, those tax structures to apply to this industry, which we think could help accelerate the entire industry. And that's really our goal here, is not to, be the one player, but to accelerate everything that is happening in the lunar environment, and certainly within the kind of ex-Terran economy. So, this really aligns kind of national interest, and this applies both to Canada as well as kind of other countries around the world. We fundamentally believe that, like, the technologies related to space mining, so, solar power, battery storage, water processing, hydrogen storage, these are all fundamentally the same technologies for fighting the climate crisis, of the kind of new economy, et cetera. And then in a global competitiveness perspective, really, the same kind of thing. In Canada, we need to continue investing within the mining industry to keep that competitive. But all of the stuff that's going to happen with space mining, involves robotics, AI, et cetera, all the things that countries will want to be competitive in kind of going forward, and are crucial areas to kind of invest in. Within Canada, it kind of plays to our strengths. It makes a lot of sense for the government to invest in space resources. As I'll get to in kind of the next slide, we think there's this diverse economic impact. So, I call it the galactic supercluster effect. I mean, if you look at kind of space resources and all it represents, these are really kind of key, crucial areas of the economy over not the next couple of years, but the next 20, 30, 40, 50 years. So it provides a great flow in to develop all of these areas and expertise and human capital in these areas from a global perspective, and to allow countries to stay competitive kind of on a go-forward basis. So space mining is really diverse. It is not just one thing. It's interdisciplinary, and that's, I think, from an economic development standpoint, really what makes it fascinating. So as a path forward, we're all about a collaboration and cooperation. So we think, obviously, nothing gets done alone in space. So it's about the cooperation and collaboration. The ISRU value chain is really large and complex. And so, this is a world problem we all need to solve. This isn't a problem for any one country. This is a problem for humanity. All of the space businesses like additive manufacturing, space hotels, tourism, all of this stuff is going to require resources and a new supply chain off planet. Most likely in the near term, that's coming from the moon, right? So it's not just water and oxygen. At later points, it's going to be, other base materials, aluminum, silicon, titanium, et cetera, that are going to be needed for manufacturing in space and for building out that new supply chain. So this is a big problem to be solved for all of humanity. Interoperability and design standards, like, we have to work together to ensure that we are creating systems that work collaboratively and cooperatively. It would be a huge mistake to not ensure that we have proper design standards for interoperability on a go-forward basis. We should be learning the lessons of the past in space, and ensuring that we can maximize interoperability where it makes sense. And then, back to that kind of retooling oil and gas, we think a lot of this at a global level, countries and companies should think about leveraging and retooling existing industries and existing infrastructure. There's a lot of stuff out there that could be applicable to space mining that may not logically be connected to space mining right now, but can be. And we think that's a part of this story. This is about kind of refurbishing existing industries and retooling them on a new goal. We'll just finish with this quote: "Make no little plans. They have no magic to stir men's blood." That's by Daniel Burnham. He is the architect of the Flatiron Building in New York, as well as Millennium Park in Chicago. We're going big and going big for a reason. This is a key problem for humanity, and we think it's in everyone's interest to solve. With that, I will stop sharing my screen. Feel free to reach out. We're looking for partners. We're looking for capital. We're looking for people. We'd love to work with any and all of you.
That's great, Daniel. Very interesting presentation. I agree. Canada has a lot of potential for this because of their long history of mining. And Australia does too. Our next speaker is Gary Callan, who's co-founder and CEO of Lunar Industries. It's a space technology startup focused on developing, building, and operating metal foundries in space. And I think he's got an interesting concept because he's going to be talking about how do we mine stuff that we put up there already. So in this role, Gary's applying his diverse background in entrepreneurship, capital markets, and corporate finance to build a key component of the emerging cislunar industrial economy. He's got a BA in economics from the University of Colorado and a charter from the CFA Institute. He took action with his lifelong passion for space by completing the ISU Space Studies program in 2017 and now he strives to help lay out the foundation for sustainable human presence beyond Earth.
Yeah, so as you heard, I'm Gary Cowan, co-founder and CEO of Lunar Industries, and yeah, I'm looking forward to. I'm happy to be here. Thanks for including me. This is an exciting, topic, obviously, and we see metal processing as fitting in clearly into the value chain for mining and using resources on the moon and in space. And right, the way we're looking at things, we have the same. I think as others on this panel, we have similarly big vision. We believe that right now we're seeing the beginning of a new industrial revolution in space, which will underpin the sustainable expansion of humanity beyond Earth. And maybe one day will lead to large rotating habitats such as the one in this image. Obviously, that's a little ways down the road, but we want to set our sights on big goals. The drivers of this current environment, we see this as being fueled by rapidly dropping launch costs and reusability, accelerating private investment, and really an intensifying geopolitical competition to put permanent bases on the moon, develop cislunar space into a viable economic zone. It seems like this has been tried before, but with the current environment the way it is, it seems as if there's real staying power for what's happening right now. So while much attention is usually focused in ISRU and space mining on mining for water, which for obvious reasons, this is going to be an important first step. For the in-space industrial economy to really flourish, metal resources sourced from space are going to be absolutely critical. Metal resources have been critical to industrialization on Earth, and they will be in space, and they need to be coming from space. Eventually, large quantities of these resources will certainly come from mining the moon and mining asteroids, but we should not overlook the material that we can derive from recycling space debris and future space hardware that has reached its end of life. This especially helps us develop these technologies that we need to lay the foundation for the future, in the near term. And regardless of the source of the material, the in-space metal processing is going to be essential to transforming these space-derived metal resources into useful end products. So with this in mind, my co-founders and I created Lunar Industries a few years ago to fulfill this critical need. And we seek to create the necessary technologies to process and provide metal materials really wherever our customers need them, eventually throughout the solar system. And this would be in space or on the surface of celestial bodies. And obviously, our long-term vision for large-scale metal processing is going to require a robust space-based economy to be commercially viable, and that's still ways out. At present, this really doesn't exist, but we can and we really must start to develop these underlying technologies now so that they're ready when this full economy emerges. And we can actually do this in a way that meets near-term needs and therefore acts as a bridge to get to this future. So to do this, we are creating right now in the lab where we're actually building this hardware, the microspace Foundry, which is designed to deliver small-scale, low-cost, distributed metal processing capabilities. This will enable enhanced debris removal, recycling of space debris, propellant production, and in-space manufacturing. And a similar device we envisioned would also be deployed on the lunar surface with some modifications to how it works, obviously. The system uses induction heating to make standardized metal rods. And these metal rods can be used as ingots to feed into downstream in-space manufacturing processes. And they can also, interestingly, be used as a propellant in metal-based pulse plasma thrusters, such as the Newman thruster and other systems that other companies are working on. Here I show sort of a rendering of the core of the system. It's really designed at this stage to be pretty small. It's about 0.5 meter in length. And here we have it shown with the Newman thruster on the end. But yeah, you can kind of get a sense of how big we're talking about here, this idea of having a distributed system. So how do we use this to get to that bridge? Well, we're going to start with, we think we can start most directly with improvements to debris removal concepts. Here we show the concept of including a micro space foundry on board a debris removal spacecraft, which enables it to actually produce its own propellant. And the way this works is depicted here. On the left, you see a spacecraft that has, it could be a debris removal spacecraft. If it doesn't have our system at this point, it's out of fuel. It would normally have to deorbit unless it's nearby a propellant depot where it could refuel. But if you include the micro space foundry and you utilize something like a Newman thruster for your propulsion, you can robotically harvest metal strips from this debris and feed it into the micro space foundry, create propellant rods, and thereby refuel your spacecraft. And based on our early calculations, we've determined that if you're doing a LEO debris removal operation, you really need less than 10% of the mass of any object to be converted into propellant to be able to deorbit that object down to, say, 200 kilometers, and then return to any altitude in LEO and go on to the next one. To add a little bit more description of this mission profile, I sort of show the concept of operations here. We would launch the spacecraft up with the micro space foundry on board. It would capture that first piece of debris, process that material, take it down into orbit. We can change inclinations as needed to adjust the RAN for the specific orbit that we're in. And then we can go back up to the next target and just do it all over again. And in this way, we think we can get, something like, really propulsion propellant no longer becomes the limiting factor for this deorbiting mission. But of course, this is still just dropping things into the atmosphere. We see the next step of this, taking this one step further, instead of deorbiting objects, we can actually recycle them and thereby completely remove these objects in any orbit, not just LEO, by transforming them into resources. We do this by putting one or more, depending on the amount of throughput that you think you need for the application, space foundries on a partner platform. Something like an Interax Outpost or an Axiom Station or Arcasys or whatever, some commercial platform that we can host it on, and then we send out spacecraft, debris removal spacecraft that have the ability to utilize metal propulsion to go out and retrieve space debris and bring it back to the station where we can process it and recycle it and turn it into materials for propellants and even for building large structures. And this removes it's really the only way to remove objects from higher orbits. Right now, there is no way. They present a collision hazard even after they've been placed into their graveyard orbit. And they're vulnerable to inspection and other things from adversaries. This kind of solves that problem while creating a cache of materials for future use once the economy is there. We also have the ability to, in this kind of scenario, to salvage components, to store components on the platform for later use and reuse just as they are without having to reprocess them. Let's see. So early on, just to give you an idea of the amount of potential material out there, when we were trying to figure out the feasibility of this concept, we decided to narrow it down to upper stages. Both because they are, sort of simpler and more high, they have higher composition of metals that we want to target, but also because, studies have shown that the upper stages, the large upper stages in particular, are considered to be some of the most dangerous debris objects out there. And if we were to remove, a relatively small number of them each year, it would help a lot to stabilize the debris population. Obviously, this is sort of accelerating as we launch more and more satellites in orbit, but we did look at it, and based on the space track data, we found that for large upper stages, you had 1.2 million kilograms of materials in LEO across around 800 stages, and in GEO we had 380,000 kilograms of material, and this was only what was listed. So there's obviously, as we understand, there's a fair amount more than that, but this is just what we were able to find on the public database. So when we go beyond this even a little bit further, and we start to look at other aspects of how we can use the micro space foundry, we really see a lot of different applications for where the space foundry could be used. we expect to have multiples of this on the lunar surface, or a lunar version of this, or a version that's in the gravity well. We see it being used for asteroid mining missions, where you can process part of the asteroid and turn it into propellant to return the materials. Obviously, we already talked about the debris removal and propellant processing. And interestingly, we see even materials launched from Earth as being useful. If you have another version of the Space Foundry that's not just producing ingots, but rather is operating in a continuous mode, you can use the same system, the same concept to create very large structures that could then be assembled into trusses and the like, and that could be fed with feedstock that's launched from Earth as well. So really, we're sort of feedstock agnostic, and turning this into materials that can be used to develop this economy. And so thinking about, kind of understand the economics of this concept of each of these devices. Obviously, there's a variety of use cases, but we decided to just look at the very basic idea of propellant, or of material value. And thinking about it in a LEO context, based on our calculations, we've figured out that one micro space foundry that's at only 6U in length can, with 1 kilowatt of peak power, can produce around 1.5 kilograms per hour. This would be 6 of our sort of standardized rods that we have conceived of. And then if you apply a 50% efficiency to that, you end up getting a production capability per year of around 6.5 tons. And then if we apply a $2,000 price point, was sort of based on discounted LEO launch costs, which obviously that moves up and down depending on how launch costs go. We're looking at over $13 million just for each unit in material value alone. We can add value to those materials by creating them in ways that can only be done in space, or selling them for propulsion in scenarios where that's necessary. There's additional ways that this system creates value. So we think that it does show a way of creating a feasible business case here as well. And also, because we're trying to target a smaller scale, smaller form factor, the roadmap to achieve this is much more achievable and lower cost to get off the ground. And to that point, our roadmap, as we look forward, how we get to the end game here. Right now, we're working on our lab bench prototype. We have a NASA SBIR that we're working on for studying recycling metals in space using this system. We are planning to have a full-scale lab bench demonstration of metal going in one side, making rods, and then sending that down to our friends at Newman Space to show that we can make propulsion from it. So we could show metal in, propulsion out. Then we hope to move to a parabolic flight to demonstrate the capabilities of shifting the structure into something that could function in extended microgravity. We want to do an ISS demo of sort of our minimum viable product in 2023. And we're also thinking about a lunar demo of a very similar system as the ISS version in the 2024 timeframe, with a first commercial version of this device ready in the 2025 or so. And that lines up well with the companies we've talked to who might be interested in using this kind of technology, who are doing debris removal. This fits with their time frame. So we think that there's a really solid chance that this all kind of comes together, well. And as the other speakers have said, like we also believe that we're not trying to do everything ourselves. That it's absolutely essential for all of us to cooperate and collaborate on this to make it a real robust industrial economy. And our focus is on metal processing and finding ways to use metal processing systems to turn these resources into this key critical piece of the puzzle. So with that, I will pass it on to the next speaker. Thank you.
Thanks, Gary. Very interesting. I'll be interested to hear what Chris Johnson has to say about the legal issues associated with cutting up other people's or other countries' satellites.
Yeah, only with their permission.
Well, even with their permission, it's kind of problematic under the OST. So our next speaker is Dr. George Sowers. George has 30 years of experience in the space transportation field, during a continuous span working for Martin Marietta, Lockheed Martin, and United Launch Alliance, including Extend as Chief Systems Engineering for Atlas V development. Sowers helped develop more than a dozen launch systems. He recently retired from his position as Vice President, Chief Scientist at ULA, where his team developed an architecture for fully reusable in-space stages fueled by propellant mined, refined, and distributed in space. He has a bachelor's degree in physics from Georgia Tech and a PhD in physics from the University of Colorado. And George is a fellow with the American Institute of Aeronautics and Astronautics. George.
Thanks, Rand. Appreciate the introduction. Before I dive in, I'd like to just take a second and plug the Space Resources graduate program at the Colorado School of Mines. Back in 2018, we rolled out the world's first, and it's still the only graduate program in space resources. It's fully online, so you can be enrolled from anywhere around the world. We currently have students from 5 continents, and I think we're up to 23 different countries. It's a multidisciplinary program. You can get certificates, masters, and PhDs. And some of the other panelists on this on this webinar are actually students in the program. So I'm going to talk about lunar ice mining, propellant production, and distribution. And I appreciate John Mankins for teasing this presentation a little bit. So one of the great discoveries of planetary science in the last several decades is that water is ubiquitous in the inner solar system. It's at the poles of Mercury. We know it's abundant on Mars. It's contained in hydrated minerals in near-Earth asteroids, and it's also at the poles of the moon. And the fact that water is so abundant is very, very fortunate for human exploration of the solar system. It's essential for life. It contains oxygen for breathing air, and it makes a great radiation shielding. But what I'm going to be talking about is splitting water into oxygen and hydrogen, then liquefying them into liquid oxygen, liquid hydrogen propellants, or using water directly as propellant with either steam propulsion or plasma propulsion or other means. And I've been saying this for a few years now. Water is the oil of space, and hence it's going to be one of the cornerstones of the space economy. So water on the moon exists in permanently shadowed regions, PSRs, near the poles of the moon. The low obliquity of the moon results in constant grazing sunlight. So you have these regions at the poles, crater bottoms essentially, that never see sunlight. They act as cold traps. So if you've ever had volatiles on the moon that migrate their way into these locations, they get frozen and stuck for billions of years. The existence of water at the lunar poles is confirmed by many remote sensing data sets. You can see neutron spectrometer data on the chart on the right. It was directly confirmed back in 2009 when we crashed a Centaur, one of my Centaur upper stages, into the Cabeus crater with a direct measurement of 5.6% ice by weight. And then here's a pretty famous picture of surface ice indications of up to 30% ice from a paper by Shui Li back in 2018. Now, unfortunately, all of these data sets are subject to interpretation. Before you can really economically extract ice and turn it into a business, we must characterize it as what's known in the industry as a proven reserve. This requires detailed knowledge of the extent, the richness, the distribution, and the geotechnical properties. You need to know what the ice is like and how much is there so you can design systems to extract and process it, and also develop business cases in markets. This is going to require ground truth. We have to get prospecting vehicles down into these deep, permanently shadowed regions. One of the challenges down there is going to be power. You have no sunlight since it's permanently shadowed. These two pictures show a concept that we developed under a NASA grant with a student-led team last year with a laser power beaming station that you would put on a crater rim. in the sunlight that would receive power and transmit it to a receiver on a rover in the permanently shadowed region that would then be doing detailed mapping. But it's imperative that we get that detailed knowledge before we can really determine if we have a business case for ICE. So John talked about this a little bit. I've worked on a concept that uses reflected sunlight to heat the surface of the moon. We've shown through some proof of concept testing at the School of Mines that that's actually effective. If there's not enough ice on the surface or in the near subsurface, there are other methods that are passive, like implanted conducting rods that would conduct heat into the subsurface and allow vapor to escape to the surface. That actually enhances sublimation rates substantially. We've done some proof of concept testing at Colorado Mines that shows that this actually works. Using a lamp to simulate the sun and preparing icy regolith simulants that we then placed into a cryogenically cooled vacuum chamber at School of Mines. We showed that surface ice is absolutely rapidly sublimated by this, and we can actually penetrate the subsurface to a certain extent. How far into the subsurface is right now TBD and is limited by the size of the samples that we've been able to test. One thing I'm excited about is that I've been able to find some money to start up some more testing along these lines later in the summer. So ice extraction is just one part of a bigger architecture that is part of a propellant production system. I did a lot of work on this architecture as part of a NIAC grant a year or two ago. These colored boxes show the various architecture elements. Ice extraction over here in green. There's a number of different rovers. There's the water to propellant processing system. So once you have water, you need to purify it, electrolyze it into hydrogen and oxygen, and then liquefy it into propellants. Then there are a number of other systems. The good news here is that NASA is actually investing some early technology money into some of these elements. And I'll just highlight down here in orange, with the water to propellant processing system, Paragon Space Development Corp has a contract with NASA to look at both purification and electrolysis. Colorado Mines is supporting Oxyon on a tipping point contract to look at solid oxide electrolysis. This is using the same technology that's currently creating oxygen on Mars with the MOXIE experiment. And then Blue Origin has a tipping point award that's looking at the liquefaction side of it. Okay, so that's all on the supply side. There were some questions in the chat already about markets. I've spent a lot of time thinking about propellant markets. Back when I was at ULA, I actually made a public offer to buy propellant in space, and stimulated at least a little bit of interest. I'm very confident that propellant markets will exist once we have a supply, because it all comes down to the rocket equation. And what the chart shows is without refueling, you had this horrible exponential increase in propellant mass required to go a certain delta V. You can see the benefit of one refueling or two or three. So that exponential increase, which we know is the tyranny of the rocket equation, becomes linearized. So refueling is truly a game changer. And anything we do beyond low Earth orbit, every single mission or activity benefits from refueling, whether it's civil or military or commercial, international, every single mission will benefit. And I see an eventual transition to a completely refuelable water-based ecosystem for transportation in space, whether it's using water directly in terms of steam or plasma, or for high thrust and high ISP applications or high thrust applications. using LOX and hydrogen. One prerequisite for this is that we need a refuelable transportation architecture. Again, the good news here is that every single rocket company that I know of is currently studying and planning to incorporate refueling, whether it's SpaceX or Blue Origin or my former employer, United Launch Alliance. And NASA recently has invested several $100 million in demonstrations for transferring in space cryogenic propellants. So the cost model that I've been using for the last 4 or 5 years is shown on this chart. If you're trying to bring everything from Earth, that tyranny of the rocket equation is reflected in these blue bars, where the costs rise exponentially the farther away from Earth that you get. On the other hand, if you can source propellant on the moon, these green bars, you can get substantial reductions in costs. And the orange bars represent the cost reduction you get by refueling launching from Earth. So just to give you an example, the numbers I've been using for the cost to land to launch mass to the surface of the moon, $35,000 a kilogram, can be cut by a factor of more than 3 if you refuel one time on the way from Earth to the moon. So it's an enormous lever. I put together some demand estimates. We're talking total aggregate demand for propellant, and this is all normalized to what it would be on the lunar surface, of almost 3,000 tons per year. So this is quite a bit higher than the 50 tons that John Makins was talking about. Most of the demand is not on the lunar surface. It's refueling upper stages on their way from Earth to GEO, or Earth to an interplanetary destination, or Earth to the lunar gateway, or propellant to fuel a Mars mission. And then I've also been in discussions with the Space Force about the potential of a strategic propellant reserve in space. So I won't go into this in detail. I just recently published a paper in the journal New Space that gives a lot of detail on business cases. The important point here is that if we stick to commercial only, you can get positive returns, but the numbers are less than 10%. I'm a strong proponent of a COTS-like public-private partnership model, where NASA can be both an investor and a customer for propellants. There's a huge benefit to NASA from doing this. And in that case, a private entity could get, north of 15% return on investment. So I think there's a business case there, and that's based on the demand that I showed previously. All right, so one of the important points is that the propellant that we're producing on the moon, most of it is not used on the lunar surface. A little bit is. There's a little bit of demand to refuel landers so that we can get back off the moon to somewhere else. A lot of the demand occurs from refueling upper stages on their way uphill from Earth, or refueling satellites in geosynchronous orbit, or in providing propellant for potential Mars missions. And so this chart kind of shows you a distribution network where you've got on the lunar surface, you've got water mining, propellant refining, you've got water and or propellant tankers that are moving that propellant from the lunar surface up to a depot at EML-1. You've got tankers that are moving propellant to a Mars mission aggregation point, notionally EML-2. You've got, in the future, water mining from near-Earth asteroids that are bringing it into an aggregation point at EML-1. EML-1 is a great location for that sort of a distribution node because it has access to essentially every Earth orbit. So it can meet the upper stages on their way uphill. It has very low delta V to access geosynchronous orbit, and you can get from the lunar surface to EML-1 with pretty low delta V compared to what it takes to get from Earth. Um, so the final piece of the puzzle is this EML1 logistics node. This is some work that we recently did under a grant from the US Air Force. I did in conjunction with a company called Lunar Outpost. But basically what it shows is essentially a propellant depot located at EML1. You've got cryogenic fuel storage tanks that, in my mind, are spent upper stages. They're repurposed upper stages that turn into propellant storage tanks. They're located behind a sun shield. And work we did at ULA shows that you can get hydrogen boil off down to less than 10% per year through purely passive means. One of those means is a sunshade. So this thing's always pointed, that sunshade's always pointed at the sun. Those cryogenic storage tanks are always in the shadow. They're also spun. So that whole right-hand side of the depot spins at a low rate to keep the propellant settled, which also enables you to reduce the boil off and aids in transfer. There's also water storage at the other end of this thing. And then in the middle, you have, electrolysis module and a fuel cell module that allows you to take water, convert it to hydrogen and oxygen. And if you need extra energy for some reason, for some other application, then you can run it back through a fuel cell and turn the hydrogen and oxygen back into water. But this node is that central piece of architecture that then now results in a overall cislunar propellant economy fueled from propellant mined on the Earth and eventually on asteroids.
Great, George. We have legal issues as well as technical ones. So our next guest is going to talk about that. So Christopher Johnson is a space law advisor at the Secure World Foundation and professor of law, an adjunct professor of law at the Georgetown University Law Center, where he co-teaches the space law seminar. He's also a faculty member at ISU and a member of the International Institute of Space Law. He's written widely on space law and policy issues and represents the Secure World Foundation at the legal subcommittee of the United Nations Committee on the Peaceful Use of Outer Space. Prior to joining SWF, Mr. Johnson works as an attorney in New York City and entered the space field in 2010 as an intern at the United Nations Office for Outer Space Affairs in Vienna during the 53rd Committee on the Peaceful Uses of Outer Space. He's also served as an intern in the Office of International Interagency Relations at NASA headquarters and as a legal stagiaire in the International Law and EU Legal Affairs Division at ESA's legal department at ESA headquarters in Paris. So he's going to tell us all the reasons we can't do this stuff. Not just kidding.
Well, thank you for the introduction. Legal aspects of asteroid mining. As an overview of my presentation, this is what I'm going to be talking about. First, I'm going to talk about the Outer Space Treaty for a few minutes, including and really focus on the rights, the obligations, and the prohibitions that exist in the Outer Space Treaty. You need to know all this stuff because it drives down at the national level. I'm going to spend just a few minutes on the Moon Agreement, just for the sake of comprehensiveness in my remarks, and then I'll really talk about how the story is happening at the national level through national approaches, through national space legislation. There is, work afoot at the United Nations level, the UN Working Group on Space Resources, and then hopefully some new insights that I can offer or some wisdom in this regulatory roadmap for asteroid miners, what you should be thinking about. So first, let's start with basics of the Outer Space Treaty, freedom of exploration and use in Article 1. And I'm only going to talk about those, I've highlighted it. This is Article 1, Sentence 1. The exploration and use of outer space, including the moon and other celestial bodies, shall be carried out for the benefit and in the interest of all countries, irrespective of their degree of economic or scientific development, and shall be the province of all mankind. So what is the subject of this sentence? Not space itself, but the exploration and use. The exploration and use shall be the province of all mankind. Keep that in mind as we move forward. Article 1 creates these great rights that we exercise and that states exercise. Sentence 2, outer space, including the moon and other celestial bodies, shall be free for exploration and use. Exploration and use. I hear some, perhaps folks need to mute their microphones. So shall be free for exploration and use. This is another great right. And in fact, the words use exist even in the title of the treaty. Further on a basis of equality and in accordance with international law, and there shall be free access to all areas of celestial bodies. Next, sentence 3, there shall be freedom of scientific investigations in space. So we have these great rights in Article 1, which the treaty creates. However, we have to mention Article 6 dealing with international responsibility. State parties to the treaty bear international responsibility for all their national activities, whether those are conducted by non-governmental entities or governmental entities. So, it is, I know that there's that great libertarian saying, the question is not who is going to, I should not be asking who's going to let me, I should ask who's going to stop me. This is the opposite. Please don't ask this in space law, because states are responsible. States have this obligation of responsibility for your national activities. They have this obligation for assuring that national activities are carried out in conformity with the provisions set forth in the present treaty. And in fact, in relation to non-governmental entities, a positive obligation of authorization and continuing supervision. States are required to authorize and supervise non-governmental entities and look at what they want to do in space. Now, getting to Article 2, and I said the treaty is a balancing of these elements. Article 2 is this principle of non-appropriation. Let's take a look at it. Outer space is not subject to national appropriation, whether it is by claim of sovereignty or by means of use or by means of occupation or by any other means. Now, this sentence is strangely phrased in that it does not clearly create a prohibition. You could say, if you wanted to be clear, you could say states are prohibited from national appropriation, but it gives this definition that outer space is not subject to appropriation. And so if a state was to make a claim of sovereignty or use space or space resources or occupy space or do other things, none of those acts legitimize or concretize or validate a national appropriation. Which is kind of a territorial appropriation or claiming sovereignty over a particular domain in the space domain. Now, we balance Article 2 with Article 1. Article 1, as we mentioned, freedom of exploration and use. Use is in the very title. However, balanced against that is Article 2. Outer space is simply not subject to national appropriation. Put those together. There's been decades of debate on what that actually means. Those decades of debate attest to the underlying argument or the conclusion that, in fact, perhaps it is not perfectly clear in the treaty. If there's all these folks who can debate about the limits and boundaries of how we can use space, although we look at how nations have interpreted their rights under Article 1, and especially through national space legislation. And we get to a point where, in fact, it is believed, and the general consensus is that we can use space resources. We cannot make claims of national appropriation, which would legitimize national appropriation, but we can certainly use space resources. Balanced against those obligations of responsibility, authorization, and supervision, and that states assure that national activities conform with international law. What about the Moon Agreement? Well, quickly, they wrapped up negotiation in 1979, but it did not enter into force until 1984. As of 2021, there's these 18 states parties of the Moon Agreement and 4 other signatories who are therefore bound to not, defeat the purposes of the treaty, even if they're not particularly bound by it. So my advice is, if you want to find, own, use, or sell space resources, maybe don't have offices in those countries until you can get more legal clarity and certainty and predictability from those governments. I also mentioned that, just note that Australia is one of those countries which is party to the Moon Agreement. Why do I say this all about the Moon Agreement? There's so many things in the Moon Agreement that don't necessarily understand in their context and how they would be applied to the use of space resources. This is Article 1.1 of the Moon Agreement that says that the provisions of the Moon Agreement shall also apply to other celestial bodies within the solar system. Therefore, the Moon Agreement also applies to asteroids and everywhere else in the solar system. When we look at later articles of the Moon Agreement mentioning common heritage of mankind, and especially Article 11.3, neither the surface nor the subsurface of the moon nor any part thereof or natural resources in place shall become property of any state, international intergovernmental organization or non-governmental organization, national organization or non-governmental governmental entity, or of any natural person. So nobody can own anything. This seems to be saying whether it's a person, whether it's a corporation, whether it's a country, really closes the door to a lot of things. You could come to that conclusion. It goes on, nothing that you do shall create a right of ownership. And yet there's the balance in that Moon Agreement that the states parties undertake to establish an international regime. The reason I don't necessarily like the Moon Agreement is because I can read it and not be certain about what it actually means, what it says, and how it would be applied. This was treaty making in the 1970s for activities that 50 years later still have yet to happen. So it is treaty making and legislation in the abstract. If we want to move forward, we can come up with better solutions. There may be elements in the Moon Agreement that we like and we can borrow from, especially on non-militarization. But as a treaty, I would say it's politically radioactive. Let's move forward with something better. That's all I'll say about that. National approaches is where we're at now. The important ones, the highlight ones, hopefully draw some common elements from these national approaches, are from the US, from Luxembourg, from the UAE, and from Japan, who all have national space legislation relating to space minerals resources. So the Title IV of the 2015 US Commercial Space Launch Competitiveness Act is entitled Space Resource Exploration and Utilization. Helpfully, it defines asteroid resource and space resources. Space resource means any abiotic resource in situ in outer space, and it includes water and minerals. An asteroid resource, number one, means a space resource. So it's helpful that it is defined it. The article then the law then moves on and says that the president, acting through appropriate federal agencies, shall facilitate commercial exploration for and commercial recovery of space resources. So a kind of mandate to foster the commercial industry. That's helpful. Number two, discourage governmental barriers and stable industries for commercial exploration, etc. So those are good elements and encouragement and mandate to governmental agencies. And let's see, what else does the law do? Asteroid resource and space resource rights. A U.S. citizen shall be entitled to any asteroid resource or space resource obtained, including to possess, own, transport, use, and sell the asteroid resource or space resource obtained, in accordance with applicable law, including the international obligations of the United States. So in accordance with applicable law, that kind of hints to the problem that we have. We don't know what agency we're going to approach. I'll get to that a little bit later. I don't mention the 2020 executive order on space resources or the NASA request for proposal on space resources, but these certainly form an important part of the context of the national space resource regulation and regulatory environment in the US. So moving on quickly, Luxembourg also has space resource legislation, quite boldly claiming in Article 1 of its law, space resources are capable of being owned. And it then has, the prohibition that no person can explore or use space resources without holding a written mission authorization from the Minister of Ministers. So that's who you would be approaching, the minister or ministers in charge of the economy and space activities. It is good that they have, at least we know who to ask. The United Arab Emirates, its federal law in 2019, defines space resources, any non-living resource present in outer space, including mineral and waters, and then has a few conditions on it subject to previous conditions. The conditions and controls relating to permits for the exploration, exploitation, and utilization of space resources shall be determined by the Council of Ministers and whoever it delegates. So the rules will be written by those ministers, And the permits, part 2, the permits referred to shall be granted by a decision of the board of directors upon the proposal of the director general. So at least it has who we are going to ask, who's in charge of creating the rules and maybe the application form for if we want to use space resources. This is helpful. In Japan, I don't have a translation of it. This is merely a quote from, I believe this is a quote from something from iSpace saying, what the law means. The law provides that Japanese private business operators shall be permitted to engage in these activities of space resources such as water, minerals, and other non-living resources in outer space. Okay, so that's all we have. That there is a regulatory framework in Japan. We don't know how will be administered just yet. And, I would not be surprised if other nations start drafting their own national space legislation. So that's the national approach. Briefly, I'll go over the international approach. Here's the Committee on Peaceful Uses of Outer Space, currently 94 member states and a number of observers. This year, the subcommittee decided to establish a working group on potential legal models for activities in exploration, exploitation, and utilization. Keywords, potential legal models. And I didn't highlight it, but let's see, they do have a work plan. So happening now, the chair and the vice chair will continue consultations in the intersessional period. That's between legal subcommittee that just ended and upcoming COPUS on the mandate, terms of reference, and method of work of the working group. And that working group will meet during the upcoming session. So COPUS meeting this year. So we don't know exactly what's going to be in that mandate, whether the mandate will be very ambitious, draft a treaty, or more modest and pragmatic. Let's have pragmatic discussions on what nations want to do. We don't know what's going to be in the terms of reference or that method of work, although the method of work likely will follow having the standard COPUS approach, having chairs, co-chairs, working groups, maybe expert groups, possibly along similar lines as they used for the long-term sustainability guidelines. So this is definitely something that we're going to need to be aware of and watch and be keenly following. I'll mention the Artemis Accords, which has, as of lately, let's see, 12 states which are parties to the Artemis Accords, and in those Artemis Accords, dealing with getting back to the moon and Artemis program activities, a section on space resources. The signatories note that the utilization of space resources can benefit humanity. And further on, the signatories affirm that the extraction of space resources does not inherently constitute national appropriation. So those 12 states agree to the following, that does not inherently constitute national appropriation. So at least there's 4 countries with national space legislation, and those 12 which at least have taken that position that space resource utilization is needed and appropriate and lawful. On those lines, I'll mention the ISEG, International Space Exploration Coordination Group, 26 space agencies. In their technical roadmap, they mentioned that space resources are part of their technical roadmap. I think that's important. So I see my time is running short, but this is the main ideas I want to put out there. Asteroid mining is explicitly permitted by some countries, 4 countries we know of. However, in the US, it's still unclear if the FAA or Department of Commerce would be the one issuing permits. We need to know that. More regulatory certainty exists today than even a few years ago, but some questions still remain. And I mentioned when I talk about space resources before, the same rules apply from the majority of the world. The same rules apply for asteroids and for the moon in terms of space resources. I think that will change. But the questions we need to ask is, what governmental agency are you going to be seeking permission from? We need to know beforehand, what is the application process? What do you need to disclose to the regulator to get your permit? How long does that application process take? How much does it cost? And from the regulator's perspective, we need to start thinking about, how is this interest or claim of space resources, perfected or legitimized? Do you just claim it and it's yours? That doesn't seem workable. Or do you have to prospect it? And maybe Martin Elvis will talk about how we are going to prospect some of these, resources. If it costs a lot to get to an asteroid, Do we have to actually arrive at that asteroid? How do you actually prospect it? What's to prevent a gold rush of claims? That's not something that we want to have. Also, regulators, not just the lawyers, but the economists, the policymakers will need to sit down and work out some of these things, along with what's the review process for the application of claims, interagency, some type of international review process, and how will national regulators enforce claims against claim jumpers. Lastly, what are the limits or boundaries of a permit? Is it time bound? If you get a permit, you can mine asteroid X or location X for a certain number of years, and when that time is over, your mining activity is ceased. Is it extent bound, meaning you can recover X amount of tons, but no more of resource X, but no other resource, meaning you can get the platinum group metals, but the water you're not allowed to take? And is it activity bound? You can mine resources on the moon, but you must sell them to Artemis partners at this price. Or are there other constraints placed on it? Those are just some of my brainstorms. Other folks will come up with other qualities or characteristics of a permit. It may be some mix of some of those. So with that, I'm going to wrap up and thank you for your attention, and I'll yield the floor. Thank you.
Thanks, Chris. This is a very important topic, and we're going to, as he said, we need to keep an eye on things as they happen in Vienna. Next speaker is Jim Caravala. He's the co-founder and chief executive officer of Offworld, building an industrial robotic workforce to undertake mining, manufacturing, and construction on planetary surfaces and in space. The workforce performs a solar system platform that will enable the construction of space-based solar power stations, propellant depots, and entire settlements. He brings 30 years of experience in visionary leadership and innovation in multidisciplinary areas such as aerospace engineering, space systems, robotics, and machine intelligence, manufacturing, construction, computer science, synthetic biology, and molecularly precise control systems. He doesn't seem to be able to focus. Jim's a prolific technologist and an accomplished entrepreneur, able to constantly identify new acceleration ramps in the technological landscape. He started his career in the space launch industry, managing launch programs, overseeing over a dozen successful orbital launches on Russian, European, and US launch vehicles. Modular satellite design, integration, engineering, program management are part of this process. He also architected major space programs, including new space agencies and launches at Surrey Satellite Technology, and is co-founder of Shackleton Energy.
Let's cut it there, Rand. I'll dive in.
Yeah,
Thanks a lot. Hi, everyone, and thanks for the opportunity to participate in this extraordinarily great collection of presentations and folks. So Offworld is building machine intelligent robots to operate on all celestial bodies in free space to undertake heavy industrial tasks in mining, infrastructure repair, construction, and other aspects. The goal being to ultimately build civilization out into the solar system and beyond. Our three underlying principles are to have a total life insurance policy for humanity, to sustainably develop life on Earth by using the resources of space, and of course, just to open up the frontier. Now, moving out into new domains has always been hard. In space, it's even harder. There's no atmosphere, no gravity that we're used to, and a whole bunch of other effects for our machinery systems and biology. In order to lay the underlying infrastructure, we can't use people at the front end, of course. We do need machines, but we also need to separate the agency of decision from the operation of implementation. So we need autonomous, thinking, collaborative machines. But we can't just export technology that we built on Earth. We need a new paradigm in industrial process. We need to break the last 10,000 years of slave and forced labor and create a new workforce that can autonomously collaborate together and build for the future. And we also need, in the space mining and space business sectors beyond geostationary orbit, we also need to be clear about what is our vision model and what is our business model. We need to be able to separate those two out and understand how we hold to our vision, whilst maintaining operations in pragmatic business operations that allow us to build forward. And as a quick mining space business mining 101 for the young folks and not so young folks listening in today, I would recommend the following. Find the planet with the most customers and start there. Build a great team and focus on something that can generate revenue from the start. If we can't get all the way to the moon initially, it's fine to choose an orbital services capability. But be clear about what you want to do at the end of your entire vision. I think it's very important to generate revenue as you go along, if you can. That consolidates your business model and adds credibility. And don't try and just aim for market sectors. Be cheeky and relentless and get customers. Even if it's for MOUs or LOIs, even paying customers, try and secure customers first. And I think the most important lesson for this decade is optimize for cost to service, not mass to orbit. The era, hopefully, of launch vehicles being priced on mass will come to a close this decade, and we'll enter a new paradigm. And I think Rand is going to tell us more about that in the coming weeks and months with some new articles. And establish lasting differentiation. It doesn't mean anything to be first to market. It's who's going to stay in the market, who stays in the game. So the chasm is reducing, and the era of space resources businesses is upon us. And so from our side, we took some of the lessons learned from the robotics era and built a new universal platform of hardened mobile industrial robotics that have modular subsystems in the context of mobility, thermal, tooling, articulation, manipulation, sensing, and other functions, and can extend the initial platform that we developed for the mining industry into multiple sectors. We're also expanding into undersea operations for plastics remediation and into space for space debris and lunar mining operations. The principles we're operating by from our engineering architecture is to reduce the cost of operations by an order of magnitude with fully scalable solutions that can basically turn conventional industrial processes on their head. And we took our context of what would be the ideal operation for infrastructure building in space, and it would be to have no fixed infrastructure to support that build, no people present or astronauts present to monitor machinery in situ, leave no environmental footprint, and minimize the use of consumables where possible. And when we brought that capability down to Earth, it allowed us to develop an architecture of a new industrial robotic workforce that can really cut CapEx and OpEx for terrestrial industries. So these are some folks on the first planet we're operating on, undertaking 19th century tasks in the 21st century, which we really want to replace with these systems going forward. And that allows us to build a new architecture of collaborative systems that can be operated remotely, that can think for themselves. And as the machine intelligence evolves and improves over the years, the level of supervised autonomy will reduce to the point where it's basically curated supervision of that autonomy. And at Offworld, we built our space program here on Earth already, and just engineer the deltas for in-space and celestial body environments. So we built the full stack from hardware, operating system, to tooling, to machine intelligence, and other aspects around this platform architecture that allows these machines, for example, here operating autonomously, to figure out the best locations of chisel excavation on a rock face. And the amazing thing about this is that when you take this approach, you can build a modular architecture that you can configure for any application and task in any sector and industry, because now the delta for your rebuild and new market penetration is minimized by an order of magnitude. The important thing operating in space for hardened industrial processes is that you need robustness across the board, both in the hardware, in your operating systems, in your sensing, and even in the communication and decision making. These systems need to operate 24.57 so that we really have a business and revenue generating model that works. And a quick aside, the space resources business is going to be a tricky game. Things are changing rapidly, and for you young folks out there, listen to what many of the old folks like me are wittering on about, and then be prepared to override and adapt and upgrade the thinking. Because, for example, what we have here, the challenge that we have here is that the propellant business for, in say, low lunar orbit here may have been completely uncompetitive for Earth-based propellant with fully expendable launch vehicles, but with fully reusable launch vehicles, in low lunar orbit, if you see on the bottom here, with fully reusable launch vehicles, ISRU is still more competitive, but it's not a big difference, and it gets even worse in low Earth orbit. So in low Earth orbit with fully reusable launch vehicles, the competitiveness of lunar ISRU is pushed back significantly comparing with fully expendable launch vehicles. So a lot of the assumptions I've made in the past were assuming an inelastic launch pricing and fully expendable launch vehicles. But as I look deeper into this, we're in a moving target game here. And that means we all of us in the industry are going to have to think harder and build further downstream services and products beyond simply accessing ISRU resources. We need to add value to be competitive and to not lose this market gap opportunity. And so make sure that we're building for the future, and that we're prepared to be competing against Earth-based propellant over this decade and the next. So it's just something to think ahead about. And bringing all that together, I mean, what we did at Off-World, as we now have several robots in the field on full test campaigns. We have a autonomous digging robot that is undertaking operations in the first ore bodies. And we also have a very high power directed beam energy robot that just completed its first test campaign. And that is the results of that have just been completed. And I can't say that this is potentially a revolution in the mining sector because of the, let's say, the strength of the rock reduction is very, very significant. And you can undertake these sorts of fractionated architectures and toolings when you have multiple robots working together. And we are expanding into several ore bodies and also into tunneling and construction operations with these robots. And as you start adding mining, excavation, processing, construction, fabrication, assembly, and manufacturing to this toolkit of capability across this universal platform, what we have is effectively the basis and the foundation for building civilization at any location in the solar system and ultimately beyond. And what you have here is a depiction of the operations architecture for our lunar ice mining deployments. where we're undertaking the excavation, the collection, the processing, separation, liquefaction, recondensation, and storage of liquid oxygen, liquid hydrogen directly from the lunar regolith. And so this is what we are now building upon for our lunar operations and our first program on the moon. And Offworld is likely either the first or one of the first companies to now have mining contract operations on 2 celestial bodies. So with that, I'll wrap up and say thank you very much for your attention, and look forward to the rest of the presentations. Thank you.
It's fantastic stuff, Jim. You know, you always have these arguments about should we send humans or should we send robots? And I've always said we're going to open up the solar system hand in claw. You know, we're going to work together.
Yeah.
So our next speaker is Dr. Joel Sercel. He's a proven space technology pioneer and team leader with technical expertise in space mission design, space propulsion, satellite design, architectural design, and systems engineering. Well, it's hard to find anybody on this panel that just does one thing. He runs an agile company where young engineers are inspired and empowered to build, test, break, and bust through technical limits, mature innovations at breakneck speed. He's also a certified KAI practitioner, the psychology of creativity, and an expert in practical methods of innovation. His expertise and leadership have been sought out by world-class organizations, including NASA, Blue Origin, Northrop Grumman, Lockheed Martin, Raytheon, the U.S. Intelligence Committee, and the Air Force. He's been awarded more of NASA's prestigious NIAC funding than anyone else. His PhD from Caltech is in plasma physics and space propulsion. He spent 14 years at NASA JPL, where he served in nearly all the technical roles and conceived the first ion propulsion system used in deep space missions to a comet and the Asteroid series in Vesta. He served as founding CTO of Momentus, a space company currently going public through a SPAC, before returning to TransAstra to fulfill his lifelong dream of working to establish a thriving in-space economy that will offer unbound potential for future generations. Dr. Sercel.
Thank you very much, Brand. I must say all the presentations so far have been incredible. So I hope I won't lower the bar too much with what I have to say today. I'm going to talk about space logistics and mining. We're really excited at TransAstra. We've joined Y Combinator for the summer 2021 cohort. Recently closed a mini seed round and have a rocket engine in test, as well as 4 different NASA funded activities related to space logistics and mining. So I have my hands full these days. I always love to talk about the great economist Neil deGrasse Tyson, who said the first trillionaire will be a person who exploits the natural resources of the asteroids. Probably the first 10 trillionaire. I think Bezos and Musk will reach $1 trillion just on the miserable resources of the moon in the 2020s. The problem that we have here starts with transportation. And that is realistically, still today, even with the low cost that SpaceX has been providing with the Falcon 9, it cost about $10,000 a kilogram to get propellant into low Earth orbit. To get it to GEO is about $50,000 a kilogram. And eventually the cost of transportation to the moon will come down, but for the next several years, it looks as though a gallon of water will continue, it'll cost at least about $10 million to get a gallon of water to the moon. So we still haven't solved the transportation problem. The resources that we're looking at from the moon are water and all other volatiles initially, and then of course aluminum, silicon, oxygen, all that kind of stuff. Same thing with the asteroids. Initially we'll be focusing on water and other volatiles. However, as we put the transportation networks in place, using that water as propellant, it will be, our economic models suggest that it will become highly cost effective to go after precious metals from the asteroids and actually return them to the Earth, and also strategic materials. So we have R&D in several different areas. A major thrust of the company is learning to make rocket propellant in space to enable massive new space economies. We really see it the way Gerard O'Neill saw it, and that is the goal is to get to the point where there are millions and eventually more people living and working in space, and moving the economy, especially manufacturing and dirty industries, off the surface of the Earth. We think that's feasible in the medium term, and it's enabled by breakthroughs in space transportation that are going on right now. Our analysis suggests that we can sell propellant at a significant savings in lots of different places. We're looking at harvesting water on the moon to make propellant. And we think we can provide a 90% savings with a 50% cost margin there. So water on the surface of the moon, you harvest on the moon. You make propellant for local consumption, for launches off the surface of the moon to get into deep space. Just as on the Earth, we harvest resources from many different sources. We see harvesting resources from lots of different sources in space as the way to go. The ultimate resource in space is the asteroids. It's been calculated by several people that there is enough material in the asteroids to build beautiful habitats to support up to 1 trillion people, 1,000 years of development of the human species. However, the asteroids that we'll be going after in the near term are those asteroids in highly Earth-like orbits where the delta V to return resources is less than the delta V of returning resources from the surface of the moon. We think that's highly effective in providing propellant to the LEO to GEO transportation market and the cislunar market. And it even wins out, I agree with what Jim was saying, it even wins out in low Earth orbit, but launch economics affect that significantly. So we have a few different patented and patent pending technologies focused on space resource harvesting. Our solar powered optical mining method of asteroid mining, which we've been doing experiments in the lab in New Mexico, here in Southern California, and in the Colorado School of Mines for years, involves using concentrated sunlight with asteroids and bagging the asteroids. We have calculated that there are several thousand asteroids in very Earth-like orbits with nearly zero return delta Vs in the size range of meters to tens of meters. And that's the initial target we're going after there. And then for lunar mining, we have a patent pending method that we refer to as radiant gas dynamic mining that uses microwave power. And we have an extensive high power microwave lab here in Southern California to heat lunar regolith to evolve the volatiles and capture them in cryotraps. And we've been doing experiments with ISRU with asteroid materials for years. This is a photograph that was taken by a researcher from Southwest Research several years ago, where he just took a little piece of a CI meteorite, put it in the bottom of a test tube, put a cork on it, and heated it up. And sure enough, you get enough sensible water to create steam in the test tube that deposits inside the test tube. In our experiments with actual meteorite samples and with high fidelity simulants from a number of different sources, we've shown that we can extract, depending on the type and the specifics, anywhere from 5 to 20% of asteroid mass as sensible water and extracting and capture. So water is a great ingredient for rocket propellant, as George Sowers ably pointed out in his presentation. Most people think the moon is the closest body to the Earth in terms of delta V. That's simply not true. This just happens to be, this is a figure that the planetary scientist Rick Binzel from MIT published in Nature in 2014, showing that in terms of total round trip delta V, to get resources from the asteroid, or to do missions to the asteroids. There are thousands of asteroids with significantly lower delta V's than the surface of the moon. And we've published refereed papers with trajectories to thousands of synthetic asteroids, and are working on, we recently received a $500,000 grant from NASA to prove our Sutter Ultra telescope technique for asteroid prospecting. And that's one of the things that's keeping me busy. There's a very sophisticated compound telescope coming together in the lab down the street from us. For those of you who are not experts in space, here's a map of the inner solar system. Most people think of the asteroids as being in the asteroid belt between Mars and Jupiter. And it's true, there's about 1 billion of them there. But the asteroid belt, the asteroids actually extend all the way from beyond Pluto to as close as 4 solar radii from the sun. And there are lots of different types of asteroids and lots of different orbits. We're really interested in the ones that have low delta V's to get the resources back from. And there's an arbitrary definition of something called a NEO, a near Earth object, which is that it has a perihelion of 1.3 AU. We don't understand why that's a designation. It's not very significant from either a scientific or an engineering perspective. But the ones that are very significant from an engineering perspective are asteroids that are in highly Earth-like orbits around the sun. These are asteroids that are in nearly circular orbits inclined to less than a couple of degrees of inclination to the ecliptic. And we've used the Gronvik-Jedicke-Botke model, which is published in Nature periodically, to model how many small asteroids there are there. And we come up to numbers in the several thousand. This is some early experiments with our optical method of asteroid mining. What I'm holding in this picture is a simulant that was prepared for us by the University of Central Florida in their Exolith lab. That's a vacuum tank that I brought to White Sands, working with a large solar concentrator there to show that we can actually drill holes in asteroids with no moving parts using sunlight to fracture the material. That's a very significant development, and capture the volatiles from that. This demonstration was critical to us winning about $3 million of additional NASA money working in this area to prove out the technology. Again, it's patented, more patents pending, and lots of trade secrets there. We're really delighted to be working with our colleagues at the university, at the Colorado School of Mines. This is our optical mining test bed that's tied to one of the large vacuum systems at CSM. In that test bed, we have the largest light bulb in the world. It's a 32 kilowatt light bulb that consumes 700 amps at 32 volts, because we've found in our experiments, it's not good to use sunlight on the Earth to do science and engineering. Instead, to simulate sunlight in space, you're better off making it synthetically. So with this facility, we can put multiple kilowatts, several kilowatts on target for optical mining asteroid experiments, and also for our omnivore solar thermal rocket test program. And we have 2 omnivore solar thermal rockets in the lab about a mile from me in test right now, and we'll be moving them to the Colorado School of Mines either next week or the week after to start full-scale high-thrust demonstrations. This is what the optical mining process looks like in operations. When we originally invented this process, so often inventions lead from wrong ideas that then with experimentation get you to right ideas. We thought that the fracture process was caused by the escaping volatiles. What we found instead is that the asteroid material is actually fractured due to thermal stress. And then the escaping volatiles actually drive the debris away from the surface, allowing excavation without contact. And then those small particles, heated by the highly concentrated sunlight, release their volatiles into the system where they can be cryotrapped for processing. So we've done lots of experiments and demonstrations there at CSM. We're excited about that. As part of this work, NASA has provided us $2 million of a contract to build engineering model hardware of a flight demonstrator of an asteroid mining vehicle that includes all the elements of a full-scale asteroid mining vehicle, but it's one that we would fly, that we plan to fly in low Earth orbit in a couple of years. I may have to adjust the volume here, but this is a video of how it works. For those of you who are familiar with our APIS asteroid mining architecture, we have a series of vehicles, Mini B, Honeybee, and Queen Bee. Mini B, the small tech demo. And I think I posted the wrong video. I'm sorry. This is actually not a video of the Mini Bee. This is actually the video of the worker bee that we're developing under commercial sponsorship jointly with NASA to demonstrate the omnivore thruster that's actually going to be flown on Mini Bee also. But the Mini Bee vehicle can be seen. The Mini Bee vehicle can be seen on YouTube and on our company website at www.transastracorp.com. This is Worker Bee, which is a commercial logistics vehicle that we're building, which is simpler than Mini Bee, and it only provides the transportation elements with the breakthrough omnivore thruster that's integrated with Mini Bee. Sorry, I've been pretty busy with what's going on and I just posted the wrong video. But I think this gives you an idea of how the omnivore thruster works. We call it omnivore because it can work with any propellant. This is very important. And so it's the Worker B1, which is the same size as Mini Bee, is designed to deploy constellations of CubeSats and mini and small sats in low Earth orbit. Worker B2 is a geo delivery system, and Worker B3 is a large-scale system designed to work with New Glenn or 2 Worker B3s in a Starship. But Worker B1 is a tech demonstration for our omnivore propulsion system, and it is also going to be the workhorse of our low Earth orbit logistics strategy. And it's Worker B1 that caused us to want to scale the company quickly and go to commercial operations very quickly. We have started taking orders for rides on Worker B1, and this is part of what's motivated the short-term business strategy of the company. Actually, Jim, I love what you said. Start off where there's business. There's about a $1.5 billion total addressable market for orbital logistics right now. That's projected to grow to $5 billion by 2025. And with Worker Bee, we'll be able to build the foundation of our asteroid mining strategy, but also have a $1 billion company based on orbital logistics in the short term. It uses a breakthrough in space propulsion. Other people have tried to do solar thermal propulsion in the past, but we have some unique takes on it. And we get a much more flexible system that can operate, the same spacecraft can operate with liquid water, with chemical propulsion like specific impulse, but a fraction of the cost of chemical propulsion because water is cheap to operate with. Or it can operate with liquid hydrogen at specific impulses approaching 1,000 seconds. So nuclear rocket-like performance at about 0.1% of the cost of a nuclear rocket. Omnivore fits in a beautiful place in the trade space. Electric propulsion is too slow, takes a year to get to the moon with electric propulsion. Chemical propulsion, the specific impulse, is not competitive. Omnivore fits right in the middle with specific impulses approaching 1,000 seconds and trip time for cargo delivery to the moon on the order of weeks, on the order of weeks for LEO to GEO transport. And we have a minimum viable product that's very cost effective in the short term for low Earth orbit. This chart just explains why Omnivore is so much less expensive than electric propulsion systems or chemical propulsion systems, and higher in thrust than electric propulsion. Here's a picture of our Omnivore thruster, which is in test right now, and another picture of the optical mining testbed that I showed earlier with that giant light bulb that I told you about that puts multiple kilowatts on target, and we'll be firing up the Omnivore with full optical heating in a week or so. This is an early picture of our lab in Southern California. We're doubling our lab space about every 6 months right now. Our head count is closer to 20 than 10 today. And what you can see on the left is the structure for the engineering model for Mini-B that is being funded under NASA development. And then let's see, all right, so why are we returning to the moon 50 years after Apollo? Huge technical advancements. You know, NASA and many other people love to say, hey, space is hard. And it was incredibly hard doing Apollo with stone knives and bear skins, barely even digital computers. But with modern engineering methods, modern digital control systems, modern digital engineering, integrated and computer-aided, integrated and test, the difficulty of getting to the moon and putting significant operations on the moon, we think has changed dramatically. Historic industrial leaders like Elon and Jeff, but not just Elon and Jeff, Rocket Lab, Stoke, there are lots of other powerful launch companies that are coming on board that are revolutionizing access to space. Robert Heinlein said that when you get to low Earth orbit, you're halfway to anywhere. We agree. We think the problem of low cost and affordable access to space is just around the corner. Three years and it becomes highly effective, highly cost effective for low Earth orbit industries. But what that does is that opens up the next wave of the need for transportation and logistics in low Earth orbit and cislunar space. And that's why Transastra is executing the first rapid step in our long range plan to move into orbital logistics right now. The 40-year distraction of the space shuttle and its false promises behind us, space is getting exciting. What's really cool, as others point out, is that the moon is not dry. Our colleague, Dan Britt and the University of Central Florida developed this model of volatile distribution on the moon that we've used to address key questions about getting propellant on the moon. Key problems is that the ice is in cold, dark craters. How do you get power? And how do you mine the ice? So I had a wrong idea a few years ago that you could build towers in craters to get to the ice because the horizontal sunlight would go over the lips of the craters. Turns out that's probably not feasible. But what we discovered in doing topographic maps of the moon is there are many permanently shadowed regions with lots of ice where we can build towers that get us up to greater than 90% illumination. So it turns the power situation on the moon from a desperate, difficult one to a situation that's roughly equivalent to the lunar, or significantly better than the lunar equator. So from total darkness to total light. The idea is that we build lightweight towers. If you go to our website, you can see demonstrations that we've done of engineering models of these towers. And we've shown that you can build towers on the moon that are deploy from landed packages 1 kilometer tall. In our work with Blue Origin, we've shown that New Glenn can actually launch towers into orbit, and then we can soft land on the moon to deploy 800-meter towers that provide megawatts of power on the moon. I really agree with what John Mankins was saying earlier. A few 100 kilowatts just doesn't hack it. We're working on demonstrating our lunar ice mining technology in collaboration with university partners in our microwave lab here in Southern California and in Michigan. And so this is the model of the lunar propellant mining outpost that we're doing under NIAC funding in collaboration with Blue Origin and universities and other small businesses. The mining rovers that we've designed and are working on, actually with Honeybee Robotics, have all the integrated mining equipment. The whole thing starts with a demonstration of the rover on the moon. And then we go to megawatt power being delivered after being launched into orbit by New Glenn. In our studies, we have prototyped tensegrity towers that have the structural efficiency to do this, so that a single New Glenn can launch this into space, and then it gets delivered by other transportation elements to the moon for megawatt power. Subsequently, we've actually found and patented, and we're doing experimental work showing that there's a much more efficient structural approach involving thin film inflatable structures. So the Sunflower Lunar Power Tower, which is both patented and pending is a critical part of our architecture. What we're really focused on here is building an outpost that grows from a small scientific outpost permanently inhabited to a lunar propellant mining outpost that enables a large scientific outpost, roughly the size of the Antarctic station, lunar hotels. And we've shown that actually there's a market for space tourism on the moon, and that the cost of transportation to and from the moon for 2-week visits is such that there are 250,000 people on the Earth that can afford those vacations. So that's a big business that drives lunar development and exploration. These are some photographs of our microwave tests. I can't go into, obviously, into all the technical detail of how it works, except that like anything else in R&D, we've run into difficulties and we've overcome difficulties and we keep moving forward. I really loved the talk earlier on the legal constraints. Right now, we have significant policy needs in the area of ethics and legality. Industry is benefiting tremendously from public-private partnership, where contractors or companies like TransAstra co-invest with the government in making things happen. We're really excited about Jeff Bezos' offer this week. We think that's part and parcel of how this has to work. And so we've got lots of irons in the fire. We're closing investment rounds right now, scaling the company and building spaceflight hardware. So that's what I had to say today. I hope that was useful for you all.
Great. Very, I mean, this whole thing has been great. All, you know, everybody, I'm exceeded my expectations and they were high. Our next speaker is Chris Lewicki, who's an entrepreneur, engineer, and near futurist focused on the economic development of outer space, as many of us are. He's fascinated by exponential technologies, integrating ideas from disparate industries and creating space infrastructure on which generations of progress can be made. He predicts that space infrastructure will extend beyond traditional concepts of technology and also include new economic systems and new mechanisms for governance of activities beyond Earth. He believes that the significant presence of humans in space will only be possible by sourcing raw materials from interplanetary space, including asteroids, the lunar surface, and Mars for construction, spacecraft fuel, and life support consumables, and I absolutely agree. So, Chris.
So I'm going to give a brief presentation today, which will probably raise more questions than answers that it provides. But my goal here is to reframe the way that we look at both space resources and their place in the space economy. Infrastructure is a key part of that, and it's something I kind of want to lead you through a discussion on today. And we grew up certainly surrounded by infrastructure. We look past it, and in a city scene like this, you see right to the horizon, and everything else is invisible to you. The infrastructure that we live with every day, we certainly take for granted, and there are parts of it that are hidden in plain sight, whether it's power distribution, communications, public utilities. Or things that are maybe a little bit softer, like emergency services or banking or security, things like that. And with space infrastructure, we really have very little. More than 50 years and billions of dollars. I would point to these laser ranging retroreflectors as the only in-space infrastructure that we have. They were placed, actually, the last of which was placed 30 years ago Friday. Or 50 years ago Friday by Apollo 15. And these are used to precisely measure the distance from the Earth to the moon. And they take no power. Any nation can use them. They require no maintenance. And they work just as good as the day they were deployed. So in a lot of ways, they're the perfect definition of infrastructure, if only there were much more of it. Certainly, there's a lot of buildings that we've built on Earth that have been serving the space industry reasonably well. But the hard part about creating a market is that in order to do that in space, you currently still need to bring nearly all of your infrastructure with you. So let's take a look at that. What is infrastructure? A simple definition is it's the foundation on which we build an economy. It's the things that we can kind of use as shared resources. It's often the things that our taxes pay for. And three main areas: hard infrastructure, soft infrastructure, and critical infrastructure. I think we're very familiar with hard infrastructure, certainly on Earth, roads, highways, bridges, those things that seem to need to constant maintenance, and the things that we realize when they're not in good repair. We don't often think about the institutions that maintain our infrastructure. And in space, we actually have, in many cases, well-developed institutions that help maintain order somewhat in space. And certainly there's a need for a lot more developed and I wouldn't say centralized, but knowing where to go for certain types of things and who is the reference bearer for standards and oversight. So soft infrastructure, we've got a great start on. But I think the one to highlight here is critical infrastructure, things that are just absolutely essential. And that's the definition of space systems. If it's not essential, it's usually not on your rocket or on your spacecraft or on your space station. And looking at those as a business opportunity or a way that your business can interact with other businesses, or a way perhaps where you can grow your business in a way that not only does it serve your own needs for your own market, but helps create new markets that you can collaborate with others where things weren't possible just from your own efforts. So this is a quote that I love from Back to the Future. I think this is at the end of the movie. And certainly just talking about how things are changing. We don't have roads in space, but there are a lot of concepts that roads build upon, rights of way, safe travel, monitored transport that kind of are in the concepts of roads. So we need to build space infrastructure that's appropriate for space. So where do we start? One thing that I would look at is, again, my definition of space infrastructure. What could we do in space so that if we fail, go out of business, or kind of change by the decades, that infrastructure is still there? Infrastructure usually is measured in decades, not in quarters or years. And the International Space Station, I would say, is maybe just on the edge of either being infrastructure or not being infrastructure. Certainly, if we weren't taking care of it, it'd be gone in a few years, just through orbital decay, if not through a number of other problems. And another big problem that we have with our investments in space thus far is it's not reasonable to expect that a startup or a small company could actually maintain and operate the space station. It's a piece of infrastructure that is kind of above the punching weight of most entities that would be out there. So maybe there's smaller parts of it that represent usable infrastructure. So what is likely that first infrastructure to be provided? And is it likely to be provided by the government? Another way to look at it is there infrastructure that's likely to be provided as a commercial service, perhaps to the government. And, we look at launch and transportation services, transport of astronauts. Those are services. They aren't really infrastructure. So maybe something we can look forward to as we build out capability on the surface of the moon. You could certainly see that landing pads would be infrastructure. You could also look at emergency services, where they're like bunkers where we could go from a solar flare, or rescue services kind of being a soft infrastructure. Those get to in-space infrastructure. But this underlying question is like, what could you build that, even if an era passes, it's still relevant? So I'll touch on that in a little bit. So as it goes to space resources and the space resource supply chain, certainly one idea that has come up and has been proposed is the Strategic Propellant Reserve. And there's a report there referenced on the bottom by the United States National Space Council user group that talks about the idea of a Strategic Propellant Reserve. And a note at the end of that, kind of as an afterthought, that talks about space age water stops. And this would be something that both would be a customer for space resources and part of the supply chain for it. It's very likely that you'd co-locate it with other economic activity, whether that's R&D activity, tourist activity, manufacturing activity. This kind of makes sense to have destinations where these things are collected. And it's something that lends itself to a natural monopoly. Infrastructure often does. It doesn't make sense to have competing high voltage power lines and competing fire hydrants. And those things that we all depend on, it kind of makes sense to have one. That's not to say that, of course, the contract for implementing those can't be done by a private company, or can't be done by multiple private companies in different areas and different jurisdictions. But this is an opportunity to build that infrastructure. And the Strategic Propellant Reserve, as an example, would probably initially be filled from terrestrial sources. But by doing that, it creates the idea of in-space refueling, starts to create architectures for it, starts to create markets, and really that expectation where I think, as Dr. Sowers had said, starts to linearize the exponential rocket equation. Another example I thought as I was looking at this this water stop, which is a 100-year-old active water stop in West Virginia. This is an example of actually a split fuel system where the fuel is sitting there in the tender in the back of that train, and the oxidizer, so to speak, is in that water tower. So whether you're with a LOX methane system, a LOX hydrogen system, a metal system, the idea that you don't have to supply all of the constituents of the fuel in one place is something that is an idea that's 100 years old, and it adapts as the technology needs. And I think we can anticipate that type of flexibility in space. This is something that in a longer presentation I'd build out and discuss kind of the Venn diagram of these things. But a key question for, I think, a successful business and certainly a thriving economy is what of your space resource infrastructure will be in common with space resources consumers who are using your resources to support other businesses. Things like GPS, position, navigation, and timing, data relay. I've mentioned landing pads. Joel has shared what will certainly be a need for megawatt power just to start on the moon and other places. So energy plants, both for production, distribution, and storage. Test facilities. We've got 0G test facilities, we've got 1G test facilities, and for a few seconds at a time, maybe a few minutes at a time, we can test things in between. So being able to test things on the way to the moon might be a business opportunity. Repair and failover is something that we build integral into our systems, but maybe this is, as Northrop Grumman is starting to show, something that we can have as an adjunct and as a business itself. As we get dozens of people and hundreds of people in space and private actors, we're probably going to have the need for rescue services. Rescue services where you don't necessarily always bring your own parachute. So this is actually a good sign that people will be able to operate with less of a safety net. But that safety net will start to be an important soft infrastructure. I mentioned emergency shelters. Being able to be present on the moon is one thing. Being able to be survivable in all possible environmental conditions is another thing. And maybe that's something that the government should undertake in building, maybe uncomfortable, very small, but hardened structures that we know we can retreat to. And don't have a flag or don't have a proprietary lock on the door to get into those places, so that we, again, have a social safety net, so to speak, on the moon and other places that we operate at. Another area in space where I think infrastructure will just be different than we're familiar with is in the virtual infrastructure, space traffic management, situational awareness, weather, traffic management, and things like maps, digital twins, knowing what the orbital debris is going to be, knowing what the meteoroid flux predicts are going to be, knowing when that transfer slot to or from your destination or maybe a docking port is scheduled to be available. These are all things that are going to represent infrastructure that's going to need to be created. And we're kind of haphazardly figuring these things right now on station, but we'll see a growing need for these. I think the most valuable question at all, and a takeaway for, like, if you can find this magic, you will be that 10 trillionaire in space, is how do you monetize your infrastructure as the business model itself? And AWS is a perfect example on this. Amazon doesn't make its money on Prime. They don't make its money necessarily on the margins in the store. They make their money on AWS, and AWS was a solution to their own problem that Jeff Bezos very smartly in the 2000s gave the direction to the company to make themselves a customer of their infrastructure so that that infrastructure can serve customers. So this is, I think, a paradigm change in the model that we've been serving space needs. Is we often lock ourselves into proprietary solutions or bespoke solutions for what is often a very, very difficult market need to fulfill that ends up being very customized. But if we can translate that to something where we have a generic solution that we can operate our own business. Think about, for example, it might be the equivalent of a space conference center where you have an arena, and that arena can host basketball games and sports. That arena can host trade shows. That arena can host conferences. It can host blood drives and vaccine drives. But the arena is the business model, and maybe sometimes you operate your own event in that arena. So this is kind of the model to think about and look for these business models that will start to come as we get more and more launch into space and we get more and more infrastructure in space. And this really is the type of business models that are going to allow every other business in space to grow. So that's the end of the thoughts that I wanted to share today. I'll keep them brief and looking forward to feedback from folks. This is a new topic for me. I've created a Twitter account out there and have started using a hashtag space infrastructure. Follow Space Infobot, which is an automated Twitter bot that I've set up to help kind of give a channel for things that relate to space infrastructure. And while I'm focused mostly on the infrastructure that's in space when we get there, there's still a lot of it here on Earth that helps leverage our company and business as well. So thanks for your attention today, and looking forward to the panel discussion on all the great topics that we've heard today.
Yeah, thanks, Chris. This is a subject that's near and dear to my heart too, that I've been giving a lot of thought to over the last decade or so. And I'm glad to see that other people are thinking along the same lines. Our last, and certainly not least, presenter is Dr. Martin Elvis. He's a highly cited astrophysicist with over 30,000 peer citations, has used most large space-based observatories to publish some 450 papers on supermassive black holes, seen as quasars out to the edge of the universe. Lately, concerned about the growing cost of space telescopes, he's turned to researching the astronomy needed to enable asteroid mining with a view to cutting those costs radically. He's published widely on issues related to asteroid mining and the space economy. He is unduly proud that he is probably the first professional astronomer to visit the Harvard Business School on business. He obtained his PhD in X-ray astronomy in 1978 in the UK, has worked at the Center for Astrophysics at Harvard and Smithsonian ever since on a series of space X-ray telescopes, culminating with the Chandra X-ray Observatory. He's a fellow of the American Association for the Advancement of Science, a member of the Aspen Center for Physics, and is past chair of the Hubble Space Telescope Users Committee and of the High Energy Division of the American Astronomical Society. Asteroid 9283 Martin Elvis is named after him, and we're very honored to have him here today.
Thank you. I'm going to talk about prospecting these great resources we have in space because, whoop, another thing, there we go. They are vast resources, totally dwarfing the plausible available materials we have on Earth, but they are elusive. They are not easy to find. You would think they are, but not. I'm going to talk about asteroids first and then the moon, because the moon is the more near-term example. So asteroids. We've heard a lot about it. Asteroids come from collisions between planetesimals, and planetesimals are objects from the beginning of the solar system that differentiated through radioactive heating into, like the Earth, into a core, crust, and a mantle, and then got broken up. So the asteroids we see are typically more or less pure core, pure crust, or mantle. The core is metallic, the crust is silicate rock, and the mantle is full of carbonaceous materials because it never got heated up much. Okay, so there's the two pieces of interest are the metallic iron core and the carbonaceous crust, because the core is rich in precious metals, or can be rich in precious metals, not all are. Those precious metals are worth about $50 million a ton on the Earth, and that's great. So why don't we go after them? Because it's the richest of them still only has about 30 grams per ton of these precious metals. So it's a big energy intensive extraction process at the asteroid, which is a demanding technology for now. Instead, the carbonaceous crust can be up to 10% water. It can be bone dry, depends on the asteroid. And in space, that has historically been worth about $50 million a ton. And as we just heard, the cost, of course, is coming down as launch costs come down. So this is an interesting question. The problem, of course, with that is right now there is no one on to buy it in space, and so we've heard a lot about developing markets for that. So I won't go on any more about it. But the key point I want to stress about asteroids and in the moon too is that not every mountain is a gold mine, as you're well aware. Neither is every asteroid rich in any of these resources. About 85% of asteroids, of meteorites, and thus of asteroids, are stony and not very interesting. They eventually may become sources of material, valuable material, but not the first. That's not the first place you look. It's really the 5% metallic and 10% carbonaceous asteroids that are the interesting ones. And of those, in each case, only about a quarter of them are rich in either precious metals or water. Right, so we're looking at 1 or 3%, depending on what you're looking for, of all asteroids are worth going after. And the ones we know about, Joel, I think, emphasized we must go for low delta V objects, like ultra low delta V objects. Right now, only about 3% of even the near Earth asteroids are accessible to current rockets, meaning you can get a decent sized payload there, at least a ton. That's what was sent to Bennu, for instance, on OSIRIS-REx. And that means that the numbers right now that are actually accessible and worth more than $1 billion is something like a couple of dozen. And that's of the ones we now know about, right? That isn't the total that's out there. My estimate is that that will grow because of surveys and because of better rockets, notably Starship, that by about 2030, we'll have about 400 of them. And by then also, we will know which ones they are. At least a good guess at which ones they are, as I'll get to in a moment. So first, we have to find the key rocks. So there's going to be 2 important surveys coming up. NASA is going to launch the Near Earth Object Surveyor in about 2025 for a 5-year survey mission looking for near Earth asteroids. Its motivation is to find the dangerous ones that could destroy civilization, which would be, not a good day. But there's a side use in that survey data will also find all the carbonaceous asteroids, which tend to be very dark, darker than fresh asphalt. And so very hard to see in reflected sunlight. But they're going to look in the infrared, 5 to 10 micron radiation, if you want to know, where they glow brightly from their black body radiation. This will give us the most likely water-rich objects. The orbits will be accurate from this, and they'll get sizes to, I think, around 10%. I need to check that out. And they will find all the asteroids, near Earth asteroids, down to about 50 meters in diameter. And so that's very good for water resources. Of course, there are many smaller ones, and Joel emphasized this, but they will only see those if they come very close. The other big survey, which was delayed by COVID, it should have started this year, but will probably start in 22 or maybe 23. Chile, where the telescope is situated, was hit very hard by COVID. And telescopes and work on new telescopes shut down for a long time. It will perform a legacy survey of space and time, which will cover the entire sky every night. And the system is designed to find asteroids, among other things. It will be a 10-year, it will be a 10-year mission, not 28, it'll be 32, excuse me. Being run by it's being funded by NSF, National Science Foundation, at the National Optical Infrared Laboratory. And this is different. It's going to find, it's looking at a reflected sunlight, so it finds the high shiny asteroids, the high reflectivity ones. It will use 5 different bands of the optical spectrum to image the sky, so you can get the colors of things. And that's very good for picking out the stony asteroids, the large fraction of stony asteroids. Because if you look at the spectra of asteroids, this goes from in the blue on the left to the infrared on the right for all these different types of asteroid. The stony ones are at the top, and you see they all have this characteristic flattening at the longward end, the red light end, where the red light is suppressed relative to the blue light, and that's characteristic. And it's absorption due to silicate rock, and it allows us to throw them away. Asteroid scientists will be very upset by that. You don't throw away such lovely data, but from a commercial point of view, it simplifies our search by factors of about 5, which is great. You put the two together, by the way, they won't quite see exactly the same objects, but that will give you a good measure of albedo, which again will tell you if they're particularly dark. That will show them up very well. And after that, that'll be great. That'll be a great time to be doing in situ prospecting. We won't, from the size and the type of asteroid, you get an idea of how much mass is in that object. You don't have an idea because 80% of an asteroid is typically void because it's a rubble pile, it's just empty space. So you really need to measure the mass by going in and with a small spacecraft and seeing how it accelerates towards the object, the asteroid. And you also need to measure in detail the actual water content or the the platinum group metal content. There may also be ways of doing that from a smallish telescope in Earth orbit. 1 to 2 meter infrared spectroscopy mission would be an interesting thing to look at, either privately or publicly. Now, the moon. The key thing about the moon is it's not just all the resources are concentrated into quite small areas, just a few kilometers across. So it's not magnificent desolation, as Buzz Aldrin called it moments after stepping onto the moon on Apollo 11. We've made this little table of the possible resources available with my collaborators, Alana Krodakowski and Tony Milligan, based very much on the review by Ian Crawford, by the way, which is well worth reading. Most of these resources would be for in-space use. And the big example, which we've heard a little about already, are the permanently dark regions or craters that we heard about from Josh Mankin. They go down to temperatures just a few tens of degrees above absolute zero, 2 tens Kelvin. That makes them unique places for doing science. For instance, infrared telescopes could be hundreds of times more sensitive there. The regions are small, maybe 20 to 40 kilometers across. Just a few kilometers if you really want the coldest possible ones. Now we've heard that these regions retain volatiles from the early bombardment of the first 500 million years or so of the solar system's history, when asteroids and comets hit the Earth and the moon like together. And that leads to lots of resources. We've heard mostly about water, but other volatiles will be there. There'll be organic molecules in unknown amounts. The purest water might be in a very restricted temperature range because this plot shows the temperature and the sublimation temperature for various materials. Water is, if it gets above 110 degrees in a vacuum, it will sublimate out. So it's colder, it's got to be colder than that. And its hottest temperature anywhere through the 18.6 year lunar cycle. You very quickly get other organic molecules associated with that too. And when mercury is nasty stuff, both for personal use and bad for machinery. So you need to get rid of that. And that has a higher sublimation temperature. So it's going to be quite tricky to find the best places for this. And that will need a lot of prospecting, which is tricky in permanent darkness. The resources in general on the moon are concentrated, it's not just the water resources at the poles, but here, for instance, is a thorium concentration map from Lunar Reconnaissance Orbiter. Initially, they orbited at 100-kilometer altitude, and you've got this map of thorium abundance from the gamma ray detector there. They then orbited 3 times lower and now have about 30-kilometer resolution. And you see the clumping up of the distribution of thorium. Let's compare these 2 maps again, right? As you get better resolution, things get more clumped and richer. the concentrations get higher. So we could be wrong about the concentration of these materials. And in particular, if you look at the, say, 1 pixel in that region, which is the central red circle there, that contains a lot of topography. So there's plenty of room for much more localized and higher concentrations. We don't know about these yet on almost any scale because all the surveys of the moon so far have been global. They've scanned the entire surface of the moon to do a first order resource assessment. It seems to me that this is now the time to prospect these hotspots, the potential resource hotspots in much more detail. And if you're going to mine, you really need to get down to scales below about 100 meters, something like that, to make it plausible. We could do that first from orbit by having telescopes and instruments in general designed to not to scan the whole surface of the moon, but to point at these hotspots. And you can probably get down to the 100-meter like scale. And once you get down to there, then you've made it plausible that you can raster scan with wheeled vehicles over that 100-meter square scale area, whereas doing it over kilometer scales is getting pretty tough. So if you can do it from orbit, you do it from orbit. And that's a missing link, I think, in our plans so far for prospecting. So who are the prospectors? So right now, I've talked about government agencies for those 2 surveys, the NEO Surveyor and the Rubin Observatory Legacy Survey of Space and Time. The great advantage of that for all parties is that the data is public and it's public worldwide. It's not necessarily true that non-US agencies will make the data 100% public. That's just not known necessarily. Although there's plenty also of room for private companies to pick up on some of these areas, like the lunar orbiting hotspot measurements, or certainly the plans of Deep Space Industries and Planetary Resources to send prospecting vehicles to asteroids. This is good. Private companies, unfortunately, go defunct, which is sad, but it's just a feature of capitalism. So the big thing is that if a private company does this, then very much they are not going to tell you about it. It will be their intellectual property. It will be a way of raising funding from different rounds. And that means it may be duplicated, but that's okay. So space resources in conclusion, space resources are abundant, but they are concentrated and mostly unmapped at a scale that is useful. And how they should be prospected for depends on what we think we want to achieve in space. Should it always be public? Should it be private? Should we have public-private partnerships? And we've heard a little bit in favor of that already. And I'll just leave you with those thoughts. Thank you. And there is a book you can read a lot more about prospecting asteroids, at least, that just came out, and I recommend it. I found it quite interesting. Thank you.
Thank you, Martin. A quick question for Martin, I guess. You know, the B612 Foundation has been trying to raise money to put something, I'm not sure exactly how far in, but deep, you know, in the inner solar system, so it can look out. It's not blinded by the sun. But they're looking for planet killers. The question is, I guess, would that be helpful in terms of prospecting as well?
It would be about equivalent to the near-Earth object surveyor. Yes, they were going into a Venus synchronous orbit. They were going around, and that way they will lap the Earth and hit the dinosaur killer type asteroids that are hidden behind the sun in almost perfectly Earth-like orbits, just gradually approaching us. But they could not get funding, unfortunately. So, from our point of view, I think the job that will be done by the near-Earth object surveyor is excellent.
I'll never say never. Maybe they can.
Well, yes, but there are alternative things. They're pursuing, I think, what's it called? Synthetic tracking to find faint asteroids right now. It's probably what Joel is doing, but I wouldn't want to speak for him.
Yes, we're using a different, more computationally efficient shift and add method. The Sutter Ultra Survey has several other innovations in it that involve the use of compound telescopes in a rotate, stop, rotate survey pattern. We've innovated a new orbit for asteroid discovery, which we call pseudo-geocentric. It's a slightly elliptical heliocentric orbit that causes the spacecraft to circle the Earth in a retrograde fashion outside the Hill sphere. And Jedicke's calculations suggest that Sutter Ultra will be able to discover each year 350 times more asteroids than have been discovered since the first asteroid was discovered. We're really gratified that NASA has chosen to fund us to do a tech demo of that, which will involve 4 12.5-inch f4 reflectors configured into a single compound scope with SCMOS detectors and processing with GPUs. And with that demonstration, we think that we will be able to justify and sell a really breakthrough asteroid prospecting system, and which will find, it will prospect essentially all the small asteroids in highly Earth-like orbits. Also, it's a multi-band system for doing asteroid taxonomy, and it includes an infrared channel for doing sizing. And we think you don't need to visit asteroids to prospect them.
Okay. Yep.
But we also understand that that's controversial, and it's a very complex subject.
I guess this is sort of a panel question. In terms of economics, I've been thinking about this for like 30 years. We always have, problem's always been it's expensive to get stuff into orbit. And that problem is getting solved finally. But the question's always been, and George, had some charts on it, but it seems to me there's always going to be an issue of, if launch prices get really cheap, then at some point it doesn't, if you can get stuff to LEO very cheaply from Earth, at what point does it become economically make economic sense to get resources, to get propellant, say, from the moon to LEO? Will that ever happen? It seems to me that it's basically something we can't know the answer to until we get out there and start doing it and see what the market says. But I'm wondering if people have thoughts on that.
Yeah, I think there's the, economic reality. There's also the kind of practical logistical piece. I mean, by some, forecasts that I've seen, a Starship is a 10-to-1 refueling ratio in orbit. So, how practical, even if it makes economic sense, how practical is it to fly 10 Starships up to refuel everyone that's, run out of fuel? So you have to certainly look at some of these other things from a timing perspective, right? If you've got to refuel one in that manner, yes, maybe it's cheaper, but what does that do to mission timelines and cost and efficiency from a business perspective? So I think it's more than just kind of the raw calculus. Timing is the most important thing for business, and so that's a crucial factor. And really, creating the new supply chain off planet has to be looked at from other methods. It's really a gating factor that enables all of the other activities to happen in a scalable sense.
Any other thoughts?
Yeah, I think it's very common. I get this question a lot from people who've spent their careers in the government. From the private sector perspective, financially, there's the issue of market elasticity. And that is, as the cost of doing something drops, if it has certain market elasticity, the scale of the market increases more than compensating. Okay, so that's a little abstract, so let me put it in plain terms. There's an island off the coast of California called Catalina. At Catalina, they have wells where you can get drinking water. The reason there are wells on Catalina is because it's cheap to get to Catalina. If it cost $30 million to get to Catalina, then there would only be one scientific expedition there every 10 years, and they would bring bottled water. But because it's cheap to get a Catalina, it makes a lot of sense to harvest resources locally, because the market grows. And so, so our analysis is that every time launch cost goes down, it opens the prospect of vast new markets and vastly increases the need for space resources. Put it another way, it's completely ridiculous to consider building a hotel on the moon at $10,000 a kilogram to low Earth orbit. At $500 a kilogram to low Earth orbit, it makes sense to build a scientific outpost on the moon. Once you have that outpost, you obviously want to harvest local resources. When you're doing that, the transportation costs to get to the moon drop enough that you can deliver people to the moon for $2 million, at which point it makes sense to open a hotel on the moon and have 1,000 people living and working on the moon. So reducing cost always increases consumption.
I often think about the example of Alaska, where despite the fact that they have cheap oil there, they have to import gasoline because they don't have a big enough population to justify building a refinery. Or I'm wondering if we're going to have those kinds of issues in space.
Another way to put it is the global logistics supply chain for gasoline is so efficient that it doesn't make sense to build one locally. But they do harvest the resources there.
Well, I'm wondering if there'll be some equivalent where the resources are harvested on the moon, but processed someplace else.
Well, I completely agree with the assertion earlier that the market will determine, and the market will measure a parameter called market elasticity, and that will provide the answer. So whether we sell propellant from the moon and asteroids to low Earth orbit is an open question. With GEO, it's not an open question. And anywhere else, it's not an open question. I think we'll certainly sell propellant in those markets. And we've already taken an order for $750 million for, I won't say how many tons, but many, many tons of water in GEO to support LEO to GEO transport.
And you can see the economics of, where to beneficiate and how much active in the current terrestrial mining industry. And it very much depends. It depends on the technology. It depends on the mineralization. It depends on where the resource is. And, each mining effort is optimized on doing that part of the process that makes sense for the moment that it's capitalized. And that might not be the same answer 10 years later.
I agree. George and I had a nice conversation going in the chat channel about should you upload water from the surface of the moon or LOX hydrogen? And that's a perfect example. I mean, we don't really know. There are good arguments on both sides.
And it's going to depend on the rest of the infrastructure. Is power cheap on the moon or is it expensive? As an example,
I think we're not thinking big enough, really. That in my view, I think the way we need to think about all of this is, what do we do here on Earth? We fundamentally, people don't go out for resources in isolation. What we do is build towns and cities and communities. And we do that as a function of the availability of the entire transport equation, of the infrastructure, the propellant, the needs, the business model, and the capability. And I think the equation of how we've been looking at space is about to change, to flip on its head in every way. In that we, over the last, or all our lives and over the last 70 years, we've looked at space as a domain that's accessible through a pinhole of transportation difficulty. If the types of architecture like Starship emerge and the price to low Earth orbit drops to hundreds of dollars a kilo this decade, and potentially less as competition emerges, all of the domains in space and in celestial bodies may get closer to how we view transit to the West Coast, to, for example, in 1850 or 1875, and then in 1900 and then in 1925. I think over the next 2 to 3 decades, we will see we talk of Earth as a village. We may see cislunar space as a village in the next 10 to 20 years in terms of accessibility, and then all the things that lots of people want to do. And then we don't have to discuss the intricacies of, are we talking about propellant or water in this location or that? The biggest problem we'll have is, how the hell do we meet demand? And for 100 different products and services.
Well, historically, towns have been created around transportation. You're on a river, you're at the mouth of a river, you're at a harbor.
Exactly.
And something I've been working on recently is, again, Starship changes everything. I'm starting to think of equatorial LEO as Earth's natural harbor. Because you want as much stuff in one orbit plane as you can get it, just for sustainability and space traffic management reasons. And it's the cheapest place to get to. The only problem with it, and the reason we've never done it, is because we don't have launch sites at the equator. But with Starship, maybe we can do that. Maybe we can you could build just a steady pipeline of material into space, into equatorial LEO, and then figure out how to get it to the other places it needs to go from there.
Yeah,
Sorry, go ahead.
Yeah, I think the benefits of equatorial LEO, especially with reusable second stages, are not understood. They're massive. It's very hard to make an effective reusable upper stage in any orbit other than equatorial LEO. But once you do it in equatorial LEO, full reusability, the cost collapses. And there are complex reasons for that have to do with orbit phasing and orbital dynamics. They're complex at the undergraduate level.
I certainly think that like a lot of this thinking is based on, this tie back to Earth, but I think we're on the cusp of a paradigm shift where we move to a space-to-space economy where we're no longer tied to Earth, right? And a lot of these activities, a lot of this demand is demand that's going to be generated in the future purely in space, that it's not coming from Earth at all. And these become kind of self-sustaining organic economies that are living organizations unto themselves. And so, it's clear that we're not there yet, but we are on the cusp of that, really producing any supplies off planet, whether it's, oxygen, water, hydrolox, whatever, is the first kind of step to that. Once you get past that, what it opens up is an entirely new realm of kind of growth catalysts and possibilities.
So look, I mean, on this call, we've got, at least I'm in the company of a brains trust of folks who are covering the gamut of space mining, the economics around it, the legal aspects around it. What do we do when we're there? How do we get there, both for the moon and asteroids? If we go around the table a bit here, when do we think the first real sustainable space mining business opportunities or revenue streams from sales of product might occur? And I'm not talking to NASA, I'm talking to a third-party commercial entity.
I'll start.
Yeah, go for it.
So I am a robot guy. I started my career in interplanetary robotics at the Jet Propulsion Lab. I've always been a robot guy. I'm kind of scared about human health and safety in the space environment. It's an extreme environment for which mistakes can have fast and severe consequences. Having said all that, I don't think we're really going to see exciting, scalable activities happen in space until the human presence increases by like something approaching an order of magnitude. Instead of a half dozen humans in an American space station and a couple more in a Chinese space station, I'm excited about multiple LEO destinations, because multiple LEO destinations means more experimentation. It means more throughput of ideas and ability to try them perhaps in more competitive environments, perhaps in more natural environments, depending on that. And one of the reasons when we founded Planetary Resources, we focused on asteroids was because the US in the late 2000s had just backed away from considering a significant investment in the surface of the moon. So without that momentum, it, again, speaking from an infrastructure standpoint, it would be very hard to draft your own path to the surface of the moon and build out a business there. It's not that it's impossible, just harder than the alternative in 2009. So today, with the US reaffirming their now current interest in the surface of the moon, and certainly with the Chinese-Russian collaboration having that well within their roadmap, I think lunar surface activity has the potential to be this catalyst. And I'm just very hopeful, and I'm saying a lot of things loudly to help guide investments into things that help it scale the best for everyone. So that's not a date, Jim, but I think it is well within our capacity to be beneficiating lunar surface material by the end of this decade. And that's a lot different than, making orbital propellant depots, here between the moon, but simple things like berms, radiation shielding, power systems on the surface of the moon, all of that's made incrementally easier by using as much as we can of the stuff that's already there.
The book I mentioned, just happen to have a copy here, goes into some detail about the emergence of a market in low Earth orbit. And I agree totally with Chris that that's what will stimulate commercial sales in space as opposed to selling to NASA or someone like that. And we mentioned tourism. But I think the advent of the Axiom space station and perhaps others will make a huge difference. It's going to be much easier to do research there, and individual scientists can go up and do their own research there, which will be 10 times more efficient than having a rapidly trained astronaut. It's like having a new grad student work on your project. It's just not the same as having an experienced researcher. So I think that's going to make an enormous difference. And there are experiments on the ISS on manufacturing. We've probably all heard about the Z-bland optical fibers, which might be manufacturable, seem to be promising. Also, building human organs in space, like eventually, possibly a great way to build human hearts, and a human heart is less than 1 kilogram, so cost of transport is just not an issue. So there's a lot of very exciting possibilities that are coming on. By the end of this decade, I think we'll know which ones are going to work, and that will create the market.
So I'd like to propose that we consider the bullish version. First of all, anyone who thinks they know the answer, they should go out and make $1 trillion. But it's clear that Elon is scaling to make thousands of Starship flights in the 2020s. The objective of the launch vehicle industry is to, and the physics tells us that launch to space can drop to only 10 times that of air travel in the 2020s. When that happens, the amount of traffic in low Earth orbit will be gigantic, and there will be thousands of people in low Earth orbit all the time. I mean, this is one of the reasons why Transastra has always had the plan, which appears to be a pivot, but it's just step one in the plan, which is to accelerate our activities in low Earth orbit, why we're building Worker Bee right now. How soon we go and mine asteroids or the moon depends on what the market says. It's highly nonlinear and unpredictable because, as Alan Kay said, the best way to predict the future is to invent it. It depends on who the inventors are and who the investors are that make it happen. But I can tell you that, we're turning away investors in large numbers right now. And there's a lot of money ready to go into space. Humanity has made the decision to go into space, and the investment markets are driving that. So it could very well be that it'll happen bigger and faster than we think. And I think we should hold open that possibility. I think, you know, thinking in a 20th century way, you know, it'll be 100 years until we have, you know, 100 flights a day into space. We may have 100 flights a day into space in 8 years. And if so, there's going to be gigantic markets. The other thing is, the NASA approach to systems engineering is poisonous. It's based on 20th century technology. Remember, before we invented modern systems engineering, we built the Eiffel Tower in 1 year without computers or hydraulics. Today, with modern systems engineering, it takes 10 years to build a high-rise. What Elon is doing is just applying good, solid engineering practices and team leadership. And there are lots of people who are learning those methods.
It's more about minimizing risk than maximizing opportunity.
Right. And, you know, it's like being out of NASA and JPL now for many years. I wasn't aware how fear-based everything in government is. When you go to a meeting at JPL with a wild new idea, 10 people tell you why it's stupid. And 3 of them are gatekeepers that stop the idea.
So Joel, sorry, but just to your point, do you know how long it took to develop the mRNA COVID vaccine?
Well, it depends on where you fire the starting gun.
Okay, so in the exact fair point. I mean, 20 years of R&D, but apparently I heard it took 3 days to actually develop the vaccine itself, a period of time for testing before then releasing into the wild. But to your point, and to Chris's point, when we look at some, you spoke of 10 years for a high rise. I've heard of high rises in China going up in weeks.
Exactly, no bullshit.
Right. And they just get on with it. And I think, you know, it's imperative based. It's risk reward based. If we somehow are able to communicate the existential knife edge that we're actually living on as a civilization today, at least let's say there's a probability that we're on an existential knife edge with climate risk, with our, let's say, socioeconomic irregularities and inconsistencies. We need to move like there's no tomorrow. And we see on a multi-trillion-dollar impact of the pandemic, and how by not dealing with it collectively and aggressively, billions or tens of billions of dollars of prior investment turn into trillions or tens of trillions of dollars of cost in the rearview mirror. And we need to take these lessons on the pandemic, apply them to climate and civilization stability, and really push this message home so that we can develop forward into system of space and beyond.
I think if you look at, you know, this through the lens of like old space and the way things were done, and certainly the risk appetite of, you know, how space programs have been developed, yeah, it's going to take forever for us to get anywhere. But, you know, if you start looking through the lens of robotics and a more iterative design approach, right, and a tolerance for risk failure, you know, we assume that the missions we're going to put up on the moon are going to fail at multiple levels, and we are going to continue to learn from each one, continue to iterate. That is why I'm not sending people, I'm sending robots, because, you know, I'm assuming they're going to die. And so, you know, but between that and the amount of capital that has flowed into the space just over the past year, there's been unprecedented capital inflows. If you look at the SPAC transactions and everything else, this is really a paradigm shift in space. There is more capital. We are on the cusp of a private industry that is no longer, you know, reliant on the government here. This is not going to be led by the government. It will be partially kind of de-risked by it. And then if you add on top of that what's happening with China, right? If you had looked at the timelines for lunar development 9 months ago, they were completely different than they are now. When China landed that lander and then announced after that that they were going to build a moon base with Russia, that is a paradigm shift for exactly what happened here. So, things are changing. There are future events that we have not predicted that will be exactly like that Chinese announcement and Chinese mission that will just accelerate this in ways we cannot predict.
As long as we're talking about risk aversion and we're hawking books, somebody wrote a book about this. We'll get it to, doesn't want to too shiny or something.
Jiggle it if you wanted to. Jiggle it.
Jiggling is the problem, I think there.
What's it called?
It's called Safe is Not an Option. Doesn't want to show.
Well, it's very stealth. Anyway.
To the failure is not an option, Kip. I think a lot of the message here is that, failure is not great. And there are certain circumstances where we would like to completely avoid it. But it's not about elimination of failure or mitigation of it. It's about resiliency to the path of failure. How do you build a certain amount of mistakes and things going poorly into your plans? How do you make it okay that it doesn't work out the way that you expect it the first time? And an easy example, Elon talking about 3 launches of the Falcon 1, and he was going to throw it in. Good thing that he was able to do the 4th, because he's been able to build a pretty successful company as a result of that. So the challenge in space, I think, still is it is more expensive than other industries to iterate, but that doesn't mean it's impossible. And the best business models try to figure out what the right balance point is between that iteration and the market it's attempting to serve.
And Elon's demonstrating that every day down in Boca Chica. He hopes the rocket will work, but he doesn't expect it to.
Yeah,
and he learns every time he fails.
I think it's healthy to push back on the assertion that failure is more expensive in the space industry than other industries. So what is expense? It's work.
It doesn't have to be.
Yeah. So what is expense? It's work hours. So the rover that JPL recently put on Mars cost $1,000 a kilogram, in excess of $1,000 a kilogram of workforce. It was very expensive to not iterate that. In software, people say, well, it's cheap to fix software, but in fact, when you create bugs in software, fixing those bugs requires engineering workforce to fix those bugs. And rebuilding hardware in the space industry is only about 50%. Only about 50% of the cost is hardware. It's mostly the engineering time. So Chris, I think your point about that is very thoughtful, but I think we need to revisit that assumption. I'm not sure it's true. I think you can't plan a development project on the basis of planning for failure. What you do is you do a plan which is based on an assumption of all green lights to Malibu. All green lights to Malibu is something that never happens. And you know that, but what you do is you create a culture where failure is not viewed as a disaster and it's expected, and you're always adaptively responding.
That's my point. Rather than doing it in one huge increment, all green lights to Malibu, how do you figure out what are the increments that you can experiment on that are a better optimization of work and cost?
Yeah. And what you do is you create a culture where people are just experimenting and testing all the time and breaking things in the lab all the time. It's like when I go and visit my engineering team, I say, what have you broken lately? What? Why not?
And they say your laptop.
Let me take a question from the audience. This one's to Jim, but others can answer as well if they have one. What do you mean by service to orbit-based pricing? How does that work?
In the context of accelerating, let's say, a large-scale business in space with grand objectives, building or manufacturing is harder than service-based provision if infrastructure exists. So a service-based business might be, for example, use existing Earth imaging satellites, obtain access to their data feeds, and provide additional intelligence layers and value add on that product, which you can sell immediately to existing customers. That's something you could get up and running in a 3 to 6 month period if you understood a value proposition and a market need. So it's basically the steps are, if you can't build infrastructure beyond geostationary, beyond the market chasm, pull back, build infrastructure at geostationary or before the market chasm. If you can't do that, pull back, build infrastructure in low Earth orbit. And if you can't do that, build service either in geo or in LEO and apply it to Earth markets. So just kind of, I was alluding to reduce the scope and the size of your business proposition so you can activate business. There's no such thing as a space business. There's just business. So get going with that first and build up the extent into the space domain as the market need dictates.
We have sort of a legal question that a lot of people are asking in various ways. People who are not U.S. citizens want to get involved, and how is it? Are there difficulties with getting involved in this industry? We know there is in launch. We know there is in ITAR protected things, but is there a problem for what you guys are doing? Can you hire for us?
I could answer that very quickly before Chris might jump in. Offworld has several Offworld overseas subsidiaries. So for non-US persons wanting to get involved, there's room for growth, and we're hiring both in Europe, Africa, and Australasia.
That's great.
We don't have those issues in Canada, so come on over.
Anybody else?
We're hiring Americans.
Just to talk as the challenges of a founder and CEO of a company with U.S. laws is, well, it's not too difficult to integrate people outside of the U.S. into a business activity. For a startup, it creates a big overhead, because now you have part of your business that needs to keep track of a bunch of set of rules, maybe for one individual or two, and then you have most of the rest of your business which doesn't have that restriction. And then you have to actively spend time on being careful about the mixture of the two. And some of it falls to like facilities. You can't have same activities going on in the same room where people can get access to them. I will refrain from comment on whether any of that makes sense. It's just currently the law. And it's a little bit of the background between one of the reasons why it's generally the larger companies in the US that have enough of a footprint that are able to mix those things in. So apologies in advance on behalf of US policies for everyone else in the world who would like to engage with us American citizens.
Well, Elon's gotten caught between the gears on that himself, right? With the person who was suing him because he wouldn't hire a foreign national, even though it was against ITAR. So he's between a rock and a hard place. And here's a interesting question. Does incenting harvesting metal from holes with ships and debris in space actually incent or marauder economy, and thus the depravity of our society as pirates scavenge the stars? Let me ask you a different way. And I do worry about reavers sometimes. But I wanted Chris to respond. It's a different, one thing to mine the moon. It's another thing to mine a body that was put up by a state's party that continues to carry responsibility for it.
Gary,
how do we deal with that?
Not me.
Well, both Chris and Gary, I guess.
You're talking about Chris Johnson, right?
Yeah, Chris Johnson, multiple Chris's here. Sorry.
Oh, sorry. Yes, Chris Johnson.
I mean, as far as the first question goes, I think there's enough regulation in place around, you can't just go, even if we are creating value out of debris, you're not going to be permitted to go after something without permission from the launching state and the alternate owner of that property anyway. So we've always gone on the assumption that we would only be able to operate with permission for harvesting resources from space debris.
Well, that's the question then. How do you get that?
Yeah, I'm gonna throw one probably to Chris's side of the net. I think there is a chance that the Outer Space Treaty will come under such pressure just through the weight of precedent over the next 10, 20, 30 years that we may see either amendments or additional treaties or regulations forming that will answer some of these questions.
I think it'll happen quicker than that. I mean,
Well, Chris, what do you think?
Oh, Daniel, you had a hot pursuit response. Please go ahead.
No, just like we're already on the, I don't think 20 or 30 years, like it's already at the point of breaking, right? None of this really envisioned commercial state actors. This is all going to be resolved in some capacity. I have no idea what that looks like. Chris is the expert here, but in the next 10 years, there's going to have to be some consensus as you look at the timelines of what's happening on the moon and elsewhere.
Well, shortly I'll talk about, the debris and removing debris where we can identify the launching state. We can ask for permission. It's a large piece. We can see who launched it. That's different from the small stuff that we want to remove. We don't have salvage rights in space. We likely will need salvage rights in space. But the good news is I think that regulators are open to those types of discussions, especially because they assist cleaning up the space domain and they assist space sustainability. So long as this activity takes place in a transparent and safe and non-escalatory fashion, because there's significant security implications of having that type of technology. But I think it's possible. And then the case is easier when you can identify the launching state, which still owns that piece. In larger context about viability, future proofing of the Outer Space Treaty. Look, the Outer Space Treaty is not going anywhere, and I don't think it should go anywhere. But I always talk about the modest aspects of the Outer Space Treaty where you ask a question of it, it doesn't give a clear answer. Deficiencies in what the law is. And in that respect, that's where national legislation fills in and where we will not have at the international level new treaties, but certainly the possibility for the development of non-binding principle statements. You can look at the LTS guidelines. You can look at the IADC space debris mitigation guidelines. I predict that probably in the next couple of years, and this was answering someone's question, what will happen at COPUOS for space resources? I would not be surprised, because they operate by consensus, that the consensus that they reach is that it is permissible to do these things, and that there's going to be something that has to be offered to the rest of the international community. But whatever they develop will be not a new treaty, but will clarify, elucidate the deficiencies that we have in space law. So that's what I predict.
Here's one more. We don't have a lot of time left, but the question is about how do we keep, going from legal back to technical, how do we keep the regolith out of the habitation site because of the toxicity of the lunar dust? I assume people have thought about that.
Don't leave the habitation site.
Well, that's no fun. It's like COVID, 24/7, 365, right?
Look, guys, the airlock is going to have to be a clean room.
Yeah,
it's going to have
a dust room instead of a mud room.
Exactly. It's a practical question. That's when you build a hotel or a significant outpost on the moon, it's a real problem that we have to deal with. And but there's engineering solutions to it.
I know that our time is short, so I'll briefly make just a minute of remarks. Is that in the governance regime that we have, there is no ordering or hierarchy of activities on the moon. So your commercial activities, whether it's mining, are of the same nature, both as permissible as scientific investigations and putting telescopes and cold traps. Spaceflight doesn't have a hierarchy of it, but we will need to have a discussion with regulators and with governments as to what happens where, and the characteristics of that type of activity in a way that conforms with international law, doesn't create tensions between states. So there's a lot of discussions that have yet to happen, with and a lot of patience is going to be required, and understanding the narrative that the new space industry has and its perception, with the rest of the world, has to really be seriously thought about. Lastly, in my remarks, I mentioned that some regulators have a mandate to foster commercial space. That hook, that anchor, is something that will need to be exploited and really utilized. Find regulators that want to foster commercial space and want to say yes to your activities, as opposed to, regulators that are looking for excuses to say no. That's all.
Well, go ahead, quick.
Quickly, I think as industry, it's incumbent upon us to push back on regulators and let them know that, at this point, that is really what is holding back in many ways these industries. They are sensitive to that message, and I think that's an important message for us all to communicate in our respective jurisdictions and conversations, because again, this is a problem we all need to solve. This isn't one company's problem. This is the world's problem. That now is the time to be updating these regulations and probably iterating upon that, as things evolve.
With regard to that, let me just make an announcement that Paul Steimers, who is a lawyer at K&L Gates and a lobbyist, has done a lot of really good work writing legislation that's very helpful in this area, is starting a space resources industry group. And he's asked me to help from an industrial perspective to help coordinate that. And so if anyone it's vitally important that the right words get to the right policymakers to encourage effective space industrialization with proper stewardship and ethics. And so our philosophy is very market driven, minimum but necessary regulation as needed to encourage ethical exploitation, ethical use of the resources for the betterment of the economy and humanity. So if people are interested in that, they should reach out to me. I posted my LinkedIn there. Also, you can go to the Transaster website, use the contact form, and I'll put you in touch with Paul. I would love it if everyone on this panel would join that. And I'm inviting you to join today.
And following on from that, that's a great gathering, Joel. The Moon Village Association, which is an international non-for-profit body, has formed a working group following on from the Hague Space Resources activity for industry coordination on the lunar surface and in cislunar space around a number of aspects of standards, interfaces, operations, and best practices, which I think there's at least 30 to 40 nations represented now, and representation into COPUOS. And this, I think, is going to be a strong interaction and point of coordination. And so, the work that Joel, you're doing there with that working group as well, all of this, I think, will feed together as we start to get the results of these deliberations and coordinations. It's all very important.
Well, we're out of time, unfortunately. I could easily do this another hour, but that's a good note to end on, I think, because I think that's going to be one of the big barriers. It's probably certainly not finance at this point, right? And the technology is coming along, but the regulatory issues, the governance issues, and Open Lunar is working that as well, Jesse Kate Schengler. So that's probably a good note to end on, that we shall get more involved in helping forge the policy that we need to move forward on this stuff. And I want to appreciate again, thank everybody on the panel, and hope all the audience enjoyed it.
Thank you, Alex.
Thanks, guys.
And all panelists, if you don't mind sharing the presentations. We will actually text you about that, and we'll put them on the website because people were asking. And thank you very much. SpaceTech Analytics is grateful, and personally me for having like that you actually devoted your time here. That was great. Thank you.